This is a conversation with Dr. Sara Seager. She is a highly decorated planetary scientist, a professor at MIT, and a world-renowned expert on the scientific pursuit to find life outside of Earth. We had the opportunity to spend some time with Sara. And whether we were at the vents testing the instruments in the volcanic fog, to climbing through the lava tubes deep underground in these caves, to spending those little moments, like in the parking lot, we really got to see who Sara is. And let me just tell you that she is an incredible person. This conversation has two parts. And the first part takes place 14,000 feet up in the air on the top of a volcano on the big island of Hawaii. Well above the tree line and well above the clouds, you can see here that they have built massive telescopes that peer deep into the universe. This is a place that Sara knows well, very much on top of the world, and very much in her element.
Sara.
Zan.
Tell me about where we are right now.
Right now, we are in Hawaii on top of Mauna Kea, a mountain nearly at 14,000 feet. And we're at the home of some great observatories. We can see right behind us the twin telescopes of the Keck telescopes. We can see Subaru, we can see other telescopes.
I mean, this is one of the most incredible places that I've ever been. I mean, when we drive up here, it was raining below, and you drive up through the clouds, and it really feels as if you've broken into the sky. Tell me, what do these telescopes do? What do they look at?
They look at so many things in astronomy. Everything from super far away galaxies to like planetary nebula to planets in our own solar system to stars with exoplanets.
This is a place that you've worked before.
I have. In the old days, before internet was really useful, the astronomers, we had to come to the telescope actually, and there would be a telescope operator, but you would implement your program with the assistance of the telescope operator. And you would press like the buttons on the screen with your mouse to take the exposure. You'd press the buttons to set the time of the exposure and things like that. And I'm not an observational astronomer. I'm what's called like a theorist or a phenomenologist, like a programmer really, doing the theory side and the data interpretation. But I did spend some time here actually, and we were at that telescope back there, that shiny one, CFHT, Canada, France, Hawaii telescope, back like 25 years ago, and we stayed at 9,000 feet in the dormitories. Nowadays, we astronomers just do remote observing. We do it from our home, like from our dinner table or our office, and we can just patch in really, and the telescope operator is still here, of course. But it's hard up here. Can you feel it? Like, can you feel the air being so thin and like your brain isn't really there?
What is it, 13? Is that what you said, 13 or 14,000?
It's almost 14,000 feet.
So we are so high up, we're well beyond where trees no longer exist. And the air is lighter up here, and it's windy, and I mean, this is a harsh environment.
So harsh, and it's so hard and cold, and we just always felt like a little bit sick at the telescope. And the road is not, it's a little, not dicey, but you really have to focus. You got to pay attention on that road. It's a dirt road, like with the edge right there.
I mean, the only way we got up here is by renting a 4-wheel drive, and they wouldn't let you get past.
Yeah, there's a pass, and the rangers are checking, and they're actually instructing you on like go in your low gear, all-wheel drive, low gear, and they're telling you what to do. And if you don't have the right vehicle, you're not coming up here.
So this is an incredibly special place to tell the story of the stars, and that's something that you've dedicated to your life to.
I have.
And our conversation today is going to cover many things, and it's not just about exoplanets and your work to find Earth 2.0, but it's also about discovery a little closer to home. Can you tell us about what that discovery is and what it'll lead to?
So remember, I was studying exoplanets, searching for planets, trying to evaluate all the gases that could be a good sign of life elsewhere, and my favorite gas being phosphine. Well, we got connected to a team led by Professor Jane Greaves searching for phosphine on Venus. And do you know what? One of the telescopes that she used, it's right there.
Right here.
Yes, it's the James Clerk Maxwell telescope. It's a radio telescope in that cylindrical-like dome there. And she used the James Clerk Maxwell telescope, and it's one of the two telescopes. One's in the southern hemisphere, the ALMA array. But this is a telescope where when observers take our data that's on the archive and do their own analysis, they actually, some of them recover the signal from this very telescope of phosphine.
And tell me, why is that important? Why is it interesting that they found phosphine?
Well, it's very controversial. It's like a needle in a haystack, a tiny, tiny, tiny signal. It's like taking a photo, but seeing something, you're not sure, is it there, is it not? You have to do data analysis to draw out the signal. Did your data analysis draw out the signal, or did it accidentally amplify a non-signal? You know, that's the question people are fighting over, is whether the signal is real. So if an independent team recovers the signal of this tiny, really hard to find signal, it's a positive sign. It's still very controversial, though.
Right, but if they do find phosphine, on Earth, phosphine is almost, there's a couple few exceptions, but it's almost always created by life.
Yes, it's pretty much only made by life in any kind of quantity that's measurable.
And so if we see phosphine on Venus, then it means that there's a good chance that
there's
there
a
might
chance,
be.
let's say. There's room for...
Right. We have to be specific because lots of
really
scientists
watch our language
are going to watch this. But that's what we're trying to say, is we're trying to say that this is a chemical signal that opens a door to life being on Venus. That's a possibility, something that's really worth exploring.
Right. It's worth exploring, exactly.
Right.
Regardless, phosphine has led to this wonderful new research of us in the laboratory showing that biochemicals are stable, that some biochemicals are not only stable but form like spherical vesicles, and form complex structures. It has led to the Morningstar missions to Venus. It has led to myself and extended team coming to Venus to test our instrumentation.
Coming to Hawaii.
Did I say Venus?
Yeah.
It's the altitude. We're not.
We're at 14,000 feet.
Right.
Going to Venus, but coming to Hawaii for now.
Yeah. Coming to Hawaii to test our instrumentation to the first mission, the Rocket Lab mission to Venus Instrument, going on the drone to sample the VOG, to Yarrow and I going to the vents to use his cloud collector that he designed and built.
Let's go now to the rim of the volcano, where we can talk about finding signs of life at exoplanets and evidence for life even closer to home.
Let's do it.
So tell me about the significance of this place we are.
We're overlooking Kilauea, the volcano here, which just erupted in the last few days. My team has been in Hawaii for about a week, testing instrumentation we plan to send to Venus. And Venus is a crazy place. It's even crazier than this crater here. But one thing that we're doing is flying our instrumentation through the VOG. That's V-O-G, like fog, but with a V, volcanic fog. And we're testing our instrument to see if we can capture the ground truth of what is in the particles.
So you guys are doing experiments here that are the precursor to experiments that are going to be done on Venus.
That's right.
So let's take a step back and let's start with your story. When did you first start becoming passionate about what's outside of Earth?
Honestly, I think it's always been within me.
Yeah.
When I was a small child, I got to see the moon through a telescope. Have you ever seen that?
I have, yeah. But honestly, it's been a long time since I have.
Well, wow. I mean, if you see the moon through a telescope, it is a whole other world. And I will never forget the moment I saw that for the first time. It was just absolutely breathtaking. And a bit later, I was so lucky. My dad is not the camping type. He's not alive now, but he literally went on one and only camping trip in his entire life when he was a divorced dad. So we spent the weekends and summers with him. And one of our babysitters, Tom, wanted us to go camping, and my dad agreed. But I was even more lucky because that night was a clear night. And I woke up in the middle of the night, walked out of the tent and looked up, and wow. I couldn't believe just the number of stars out there. It was like terrifying. And then when I came back to my senses, I just couldn't stop thinking, like, why had no one told me about this? Like, you know how people tell you stuff when you're a kid? There's this, there's that.
Right.
Why didn't no one tell me about the magnificence of our night sky and of what it must mean that it's not just us here? There has to be other things, maybe other beings. Wow, it's such a ginormous space out there. And that stayed with me somewhere buried for a long time until I got older and realized I could be an astronomer for a job, one of the top 10 days of my life easily. And that's where it all started.
Right. And ever since then, it's kind of like finding your vocation.
Finding your vocation. But, there's always twists and turns. It's not like looking back over so many decades, it sounds really straightforward. But in fact, the very day I realized I could be an astronomer, I was about 16 years old, and I had just by chance happened to cross the open house at the university near where I lived, University of Toronto. Rushed home on the weekend to tell my dad how great this was. Like, wow, did you even know you can be an astronomer for a job? Then I got him launching into one of his harsh lectures at me. And he said no. You know why he said no? He said, Sarah, you have to be able to get a job and support yourself. And he's practically yelling at me and not rely on any man. It was like, wow. His reason he didn't know if astronomer could get a job. It's certainly like being a parent myself, you want your kid to go out in the world and be safe and healthy and especially like support themselves and, live on their own. So that had to stay with me for a while, but eventually I did anyway. And I think at some point, by the time I hit my mid-30s, he realized it was a good job.
Yeah. I mean, in preparation for this interview, I listened to a lot of podcasts and read your book. And I think one theme that seems to be throughout your life has been the theme of somebody telling you that it's one way. And you're saying, I'm not quite sure that's how it has to be. Right. And I think that takes a lot of, it's not easy, right? It's
not easy at all. I mean, it takes a lot. We all have a very, very special, we're all made with this inner voice, like that feeling, and some people don't even know what it is really, but I'm like this. If you're in like a dark alley in a sketchy neighborhood and someone's like shuffling up to you, like that doesn't feel right, that feels scary. It's like that, but you can have it for other things, good things. And sometimes people tell you something and like if you know someone's bad and evil and someone's like, oh, this is such a great guy. And you're like, you really have to work on that, hone that instinct.
Yeah, it's like following your intuition.
Following your intuition. And I can tell you that speaking for myself, but also it's probably for others as well, for scientists, that's how we make the big discoveries. We're on a path, we just feel it. By now, at my age, I feel it. I feel like it's almost just inside. I know this is a good idea. You've got to work on that. I'll tell people. I'll give them advice if they share what they're doing.
Right. Like
and for myself, we're investing in some new crazy things in the lab that are just so wow. I mean, we just feel like it's right.
So I want to tell the story of some of these incredibly important missions that you're on right now.
Sure.
But let's start with the backstory. So you become an astrophysicist, and what does that early journey look like?
Well, it involves high school and taking classes in math and science and paying attention, actually.
Right.
It's not just about good grades, which are sometimes really different from learning the material. You've got to really get a foundation. It means going to university and studying math, physics, learning how to program, computer programming, understanding later on, and you don't get it all at once. It turns out, okay, if you're an undergrad, I had to relearn everything many times over. Yeah, it doesn't, I mean, maybe for others, but it doesn't stick the first time.
Right.
Learning about data and uncertainties. It's funny because having kids in college now, in undergrad, it's funny, like to see what they like, how they're absorbing what they're learning, what works for them. It's funny, one of them, he's like, oh, it's ridiculous. I got taken off grades for my lab book not being complete. I just start laughing because in the lab now, you're never going to remember things from month to month, even day to day. You got to write it down.
Right.
So it's funny to see learning and looking back. Yeah, you have to relearn, absorb, own it. It takes a while. So that's undergrad. After that, it's graduate school. Just like, if you want to become a doctor, you're not done after undergrad. If you want to become a lawyer, it's like professional training at the next level. It honestly is like an apprenticeship. You go to grad school, take classes, you learn from your main supervisor. And so that's the path.
Was this path during this time, do you remember it as being mostly a positive experience?
No,
or
not at all. My undergrad, I lived at home because back, in Canada, in Toronto, you just have these big state schools. And if you live like a few blocks away, you're going to be living at home. I think at that point, I was pretty much on my own. Like no one bothered me. So I kind of liked that independence. Wasn't reliant on like rules from a dorm or not being very good in social situations. Maybe we'll get to that. It was just good to not have to deal with other students. I remember it being really hard. Undergrad was super hard, but yeah, I still liked being able to do all the things I like doing. So grad school, tough, really hard. I think, as let's call ourselves grown-ups now, you can rationalize that some things are a very long-term investment.
Right.
But when you've just come out of undergrad and you're so young, and in undergrad anyway, you're used to getting an assignment, getting the assignment done, taking a test, then semester ends. You don't have that. It's like years and years of a research project. You know, the PhD means for you to learn how to start a really hard problem that you have no idea how to do. No one has an idea, in the best case, and then you wrestle it into something. But it's hard to set out on that journey because there's no reward, there's no positive feedback, at least not in my case, and you're just kind of struggling.
So when you're going through those long hours back in that period of time, did you ever imagine you would be where you are now?
No. In fact, I was pretty much thinking of quitting grad school because it just wasn't working for me.
Right.
And part of it was my first time moving away from home, and I was kind of depressed, and I didn't have the right skills because I had to be a really good programmer, and I wasn't. I am now. I'm a really good programmer now. And I just remember calling my dad and crying, and he's like, "Oh, honey, everyone's depressed in grad school. You can talk to my, whatever, patient." Or then he'd call me back and be, "Honey, you can still go to med school now and be a doctor." Because his dream for me was to, be a skin doctor and work part-time, make a lot of money so I could have a family and have a lot of time. So I wasn't going to do that, but I was definitely thinking of other careers I could do.
Do you think that your dad telling you to go to med school maybe pushed you to do your own dreams?
No, it didn't actually.
Yeah.
But it was just, I just laughed because he had the best intentions, obviously, but it didn't make me stay in school. But by then it was almost like, we call it inertia, you're kind of moving along, and the easiest thing is to just keep moving along. Plus, one thing that is the truth is a PhD in a physical science like physics, chemistry, math, you're going to get a job. It may not be in that field of research, but they're sought after because the PhD is so hard. This ability and skill to research and start into an unknown and find a solution. That's kind of what you're being trained for. So at some point I realized I'm far enough along. Whether or not I stay in astronomy is secondary to just, getting that degree.
And so what did you get your PhD in?
My PhD is in astronomy, and it was about exoplanets. And in fact, because the story I just told you, I didn't feel like I needed to have a career in astronomy because, I wasn't super happy. And so what happened was, after I finished my first couple of years in grad school, a master's level project, I was ready for a PhD, looking around for a new topic. Exoplanets around sun-like stars were first discovered. There were about 4 or 5 of them. It was the summer after the fall when the first one was announced. And my advisor said, "Do you want to work on this?" And because I literally had nothing to lose, I didn't have to think. You meet people today, they're very strategic. They're trying to see, is this a good topic? Will this topic get me my next job? I didn't have that. So I'm wow, okay, yeah, let's do it. Let me do this.
You had a line in your book which you said that you've seen your research like a well-balanced investment portfolio of having...
Well, that's now. So back then it would be you're a 25-year-old.
Right.
And what little money you do have, you invest it all in the riskiest possible thing around.
Right.
And the chance you could lose it all. It was like that because the first exoplanets that were found, people didn't believe they were real exoplanets. The thing is that exoplanets are so small, so less massive, so fainter than their next door, the star that's hosting them. So we're doing way better now, 30 years later, but at the time, the only method we had to find planets was looking at the star and watching the star wobble due to the presence of a planet orbiting it.
So what did people think of this field?
Well, the main issue happened to be that the planets found were nothing like our solar system. All we could find were big planets close to the star, where they had no business being. Because we can see stars forming, actually, stars being born, and they have disks of leftover material that should form into planets. But there's not enough material close to the star to make a Jupiter mass object. So people thought perhaps it's the star varying, like the star pulsating. Stars actually pulsate, actually. And in fact, in this wobble method, what we're measuring is the line of sight motion. It's just one thing, the line of sight motion. We're not measuring the full three-dimensional movement of the star. So it could have been a star expanding, pulsating. And then people thought perhaps it's a little more complex to explain, but perhaps it's a binary star, because if we have a binary star, 2 stars orbiting each other, and imagine that this is a binary star, the line of sight motion is going to be tiny if it's closer to orbiting in the plane of the sky. So you could have a binary star like slightly tilted in its orbit, or you could have a planet edge on, and because you're only measuring the line of sight motion, those would look the same. So there's a variety of reasons why, and that's our job as scientists, to be skeptical. If someone puts out something crazy out there, it's the job of other scientists and their inclination to push back, actually. People do get angry, angrier than they should, but that's what happens. So in the midst of all this pushing back and people telling me, like, you shouldn't be working on this, people on my thesis committee, other professors just saying, like, why are you studying exoplanet atmospheres? We don't even know if they're real. We'll surely never detect their atmospheres, let alone clouds in the planet atmospheres. It's part of the ingredients that were in my model. And just all around me, like, no one really believed it, except the people at my university. I was a student at Harvard. My advisor and, one other main professor, they believed it was real.
So you believed it was real at that time?
Not even, no. Let me just explain it this way. Remember I was telling you the PhD,
right.
Learn how to do something hard.
Mm-hmm.
So at face value, it almost doesn't matter what you do, I'm just saying. But what I was doing was learning how to computer program at a very detailed level. And I was learning about radiation in the atmosphere of exoplanets, but it translates to our own Earth as well. Like our own climate, our sun, our atmosphere. Like I knew I was learning useful skills. And the specific discipline that I was training in, a lot of it's self-teaching by that level of grad school. Like I had no doubt my skill was going to be useful either in astronomy or earth science or in industry. I didn't mind, but were they real? Like I don't know that I was sophisticated enough to judge that.
Did you have a gut feeling?
Not really. Like
Not really.
I know it sounds
you just wanted to explore the idea.
I don't know. It just sounds like I should have been a little more on the ball, but I had no gut feeling. I had no way to have that because, but there was definitely a turning point, though, if that's what you're looking for.
Yeah. What would that be?
The turning point was when I finished my PhD and I went on to a new job, which, by the way, the new job, I didn't get hired for my thesis work in exoplanets. I was hired for a prior project that was also successful. Well, when you get your PhD, your before or after, you get to give a 15-minute talk at the annual astronomy conference, American Astronomical Society. This conference, usually the talks are 5 minutes in a session, but you get the privilege of having 15 minutes. So that was a real turning point because I went and gave my talk and it was just the tiniest group of people, like maybe one person here, another person there. They were interested in my work and asked me like to join a project or join a concept study, but it wasn't the number. Like when you think about quality versus quantity, the buzz, the like vibe in these few individuals, I'm like, okay, we got to be, if there's this level of excitement from like these complete strangers on my work and the topic, like it wasn't like, okay, immediately it's all good. No, it was a very slow evolution.
It's like a tiny signal at the right time.
It was like one of the tiny lights, the
Right.
smallest lights, just like, but small but bright. Like,
Right.
And it just sort of started slowly. I would go around giving talks and it was really interesting because instead of before, right, no one believed it. Now people started to believe it because there were more and more exoplanets being found and some were further from the star. They weren't like right up close, a little bit further away, but far enough that it couldn't be stellar pulsation. So we started getting signs that, maybe this thing is real. So then instead of people criticizing and being like, you shouldn't work on this, I would always have one professor come to me after the talk and say, if I was younger, I would work on this. So, little hint, like
That's powerful.
Every single place I went, one person, like just, wow.
So you had this thread and you're just pulling this thread, right? And so tell me about this progression of discovery here. Like how do you think about the journey of your career along trying to explore exoplanets?
Sure. Well, one thing was, and I do try to back up as well and unpack it for myself and others, because when you are successful, it's really important. Like people always talk about learning from your mistakes, but I really also believe in learning from your successes. So what happened was there are these planets, growing number of them. By the time I graduated from Harvard with my PhD, there were about 30 known exoplanets. And what I was waiting for was a special planet, one that instead of orbiting in the sky or, they all have random orbits.
Right.
With respect to our viewpoint, I was waiting for one that would transit, one that would go in front of the star as seen from our viewpoint. So these close-in planets that are very close to the star, each has a probability of about 10%. So we had about 7 so far. It doesn't mean when you get to 10 it's going to transit. It's just each one has 10%. And so I was suspected we'd get one any day because I knew who was observing and who was discovering planets, and I was ready. So I knew I should get on my project of how we could study exoplanet atmospheres for the first time. And it's like this. When a planet goes in front of the star, as seen from our viewpoint, we don't spatially resolve the star, so the light drops by the tiniest amount. We see a drop in brightness, and that repeats. But I want you to, for a moment, imagine a planet with an atmosphere. Okay, at some wavelengths where the atmosphere is very strongly absorbing, now all of a sudden the planet's a tiny bit bigger, because it's not just the dark part of the disk, it's like this tiny shell of an atmosphere. So you can imagine observing the planet at some wavelengths where the atmosphere is fully transparent. There's nothing absorbing. The planet's a certain size. Now we observe at the same time a wavelength where the planet looks a tiny bit bigger because the atmosphere is very strongly absorbing. So we want to look for a change in planet size or a change in the drop in brightness of the star as a function of wavelength. And so I'm working on this paper, working, and boom, the first transiting planet ever was discovered. I dropped everything, rushed to get this paper finished and submitted. And that paper is done. And even though at the time it was, thought of like, okay, it's too hard, 2 years later, the first observing team used my method, observed an exoplanet atmosphere. And I'm so proud to tell you today, it's the main way we observe exoplanet atmospheres.
That's incredible. And what we're talking about here is it's not the sun, it's stars way out there. Like
stars, points of light.
And it's a planet. I imagine, like, what's the proportion of that planet against a star? It's tiny, right? It's a pin
It depends. I mean, some planets, they block out 10%. No, sorry, that's wrong. Some planets block out as much as 1 or 2% of the starlight. And their atmospheres might block out 1 part in 1,000 or 1 part in 10,000. Tiny.
And that's what you're measuring.
That's what we're measuring, yeah. And it's because of the Hubble Space Telescope, the new James Webb Space Telescope. It's because of astronomy's precision instruments that we can get this job done. But let's dial back for one more second. So I got this, invented this method. Someone used it successfully with Hubble. And still there was skepticism. At that point, I was looking for a job as a professor. I was turned down everywhere, pretty much. And people would say things like, that's really cool, but here's the phrase. It's a one object, one method success. That means that there was one star bright enough, one planet that was transiting. Okay, it worked for that case, but there's unlikely to be more. I had that. I would go to some other top universities, and I remember one case, this professor said, there will never be many transiting planets. The planets that go in front of the star as seen from our viewpoint. Well, NASA had an entire telescope called Kepler, whose only goal was to find transiting planets. I myself had been working on ground-based projects to find them, and today we have untold numbers, thousands and thousands of transiting planets. So there was sort of always this hesitation, right? Always. And now this work is about as mainstream as it gets. There's maybe a third of all astronomers working on some kind of exoplanet science. And this atmosphere field is so crowded and busy now. It's so popular.
So what part of your career was this happening in? Like, take me back to...
This was happening right at the beginning of my career. Once you finish a PhD, the next step in most sciences is to get a job called postdoctoral fellow, postdoctoral associate. So the post is like after PhD. And there you have a few years to establish yourself as an independent scientist. You may still have a supervisor. You may just have someone like on paper who's your supervisor and you're on your own. And I actually had a brilliant mentor. He was very hands-off. His name was John Bacall. But that's the next stage. So I was at that postdoc stage when I did that.
And then what was life like during this period of your life?
Oh, it was amazing. I was in Princeton, New Jersey at a special place called the Institute for Advanced Study. It's not the university, it's separate. It's where Einstein was a professor, actually. But there, it was so idyllic, almost cult-like, actually. It was kind of weird. You lived in apartments on campus because it's too expensive to find a place to rent. So they set it up so you just work. You can live there, work there. You had to dial 9 to get out of your apartment, and like they deduct your rent from your paycheck. It was very almost cult-like, but it was like a Zen kind of place, like just so idyllic. You just churn through your projects, find out who you are. And with the right supervisor to give you a nudge here, you nudge there. It's amazing. I had the most wonderful, amazing mentor. It was just a good match for me. He acted like my dad. And remember how I adored my dad? So it was a really good fit. Like, he was also harsh, like a good dad, right? Harsh, but like one time I was working on an amazing paper, something I discovered. with a friend, and one day at lunch, he sits down and he's like, "So, what are you working on?" I'm like, "Well, I've got the paper I was telling you about last time. It's, I'm working on this paper. It's going to be so useful for other people who want to discover transiting planets." And he had known that I was sort of dragging my heels on this one. So he just slammed his fist on the table, stood up and said, "Well, it's not going to be useful if it's not published." And then he rushed off. So I was like, wow, instead of getting upset or offended, because, he had a different plan for each person.
Right.
I was just like, you know what, John's right. I better go now.
Yeah.
So he went back to my office, wrote all the equations up, and with my colleague, we just tried to turn that paper out as fast as we could. And it ended up being such a useful paper. I think it's actually my most highly cited paper. It's got a huge number of citations.
It's like the right push at the right time by
He
the right
was
person.
an amazing mentor, and I don't know if he knew. Sometimes people who are the very best in the world at their job, oftentimes you ask how they know what they're doing, and they don't know. Like John's job, one of them was to pick the most talented people and hire them to be postdocs at the Institute for Advanced Study. And as one of the, I had a job as it was just called a 5-year member. We were supposed to help pick the next generation that got hired. He didn't usually listen to us though. And one time we had the perfect candidate, and he came and gave a talk, and he seemed like he fit in really well. And we're like, "Okay, John, why didn't you pick this person that we thought was really great?" And you know what he said?
What did he say?
I know. Do you want to make a guess of what a boss hiring might say?
I'm maybe something with intuition. What is it?
Yeah.
Yeah.
He just said he didn't have the spark in his eye. I knew what he meant.
Right.
But I was like, wow, okay, that was a new dimension I hadn't thought of. If you're the best in the world and you've picked the most talented and trained them, and now they're all around the world in leadership positions in science, and you picked it because he didn't have the spark in his eye, it's so amazing. I'm not laughing at him. I'm just laughing because it's so valid.
It's so valid, and something that maybe our language doesn't really.
Yeah.
We don't. It's almost.
We don't have the language.
We don't have language for it.
For the intuition, but that's what he was saying.
Right.
It's really basically. And now looking back, not going to name any names, of course, and having watched this person's career for 20 or 30 years, yeah.
Yeah, I can think of people in my life, and you're like, if you have that spark in your eye, you kind of know that person's gonna.
Yeah. But it's the right match. It's not just the spark in the eye. It's the right vocation, as you said. You've landed in the right place for your skill, for your passion, and it's such a privilege to have that.
Right. Well, I want to bring it back to atmospheres for a second. So why is it important to figure out what the atmospheres of exoplanets are?
Well, in general, there's two reasons, right? I know one reason everyone wants, the search for life, we'll get to.
Right.
But one reason is just to understand the planet itself. Look over here. Our planet Earth, we're still pumping out gases from the interior.
Right.
And some exoplanets out there we think have no atmosphere, or maybe a very thin atmosphere. There are rocky worlds so close to the star probably destroyed the atmosphere by high energy particles and wind from the star. But we have some evidence, it's very sketchy though, that some of these hot super Earth, they're called, still have a sulfur dioxide atmosphere because they may be volcanically active. So how can we sort through the ideas of what a planet is? We can observe their atmospheres. And there's evidence for sulfur dioxide, and only sulfur dioxide in the atmosphere of one of these hot super Earths. And that will help us understand. And we can use models then to say, what does that mean about the interior? How much of that interior is magma? What is it like? So we need the atmospheres, the window into the exoplanet, basically. That's what the atmosphere is.
It's so fascinating how much information you can glean from it's just looking up at the stars, and you just build something here on Earth.
It really is amazing. Well, I think there was a real turning point for astronomy when people invented spectroscopy. Have you ever done this in high school, where you have the Bunsen burner and you drop sodium into it?
Right.
And then you look through a kind of viewfinder with the lines. I don't know if anyone remembers that, but that's sodium, and that's the spectrum. That's electrons in the sodium atom getting energized by the Bunsen burner, and the electrons get energy, so they jump a level. And then they drop back down, and when they do that, they're emitting photons of a very specific frequency or wavelength. And when people realize, our sun, all this light around us, you can split that light up into its constituent colors, and you'll literally see pieces missing. And each of those pieces are identified with a certain gas, atom, or molecule. Yeah.
So this is all about understanding what the fundamental chemicals are that are in
It is, but there's so many pieces missing, it would be a mistake to think it solves all our problems. But what we're really after is we want to measure the atmosphere, measure the gases in an atmosphere of a rocky world or a planet that could host life. And we want to find a gas that is way out of equilibrium, that doesn't belong. Our planet Earth, we have oxygen. We need that to breathe, right? I mean, we have oxygen on our planet. And without life, without plants and photosynthetic bacteria, we would literally have zero oxygen, close to zero oxygen. Instead, we have 20% by volume. So life has like completely changed our atmosphere.
And that's something we can identify on other planets.
We can. I mean, it's not easy, but that's the goal. Let's just call it a goal right now, is to look for oxygen in other planets. I mean, what I like to say is, if there's an intelligent civilization on a planet orbiting a nearby star, and they have the kind of telescopes we're like on the verge of building, and they look back at Earth, they'll suspect there's life here. Not from big things like the Great Wall of China, or not from pollution or city lights, but from oxygen. There's just too much of it. It's so reactive, it shouldn't be here. They'll know it has to be continually produced.
So if they look through a telescope at us, they one of these telescopes that we haven't created, and we'll talk about this in a moment, but we could create, they're going to see oxygen, and they more likely than not will be able to say, hey, that's this indicator very well that life might exist here.
But let's pretend you're that astronomer, that you're that alien astronomer, okay?
Right.
You found the sign, you're suspecting it's life, and I'm another astronomer. I'll be like, no, here's some ways it could be made without life.
Right.
And we'd be kind of that, remember that scientific skepticism, we'd be going back and forth. And so they might not be certain, but they may be hopeful.
Hopeful,
yeah.
Well, it's also the world of science where everything is different than the world of everyday life, right? Where an understanding of what is true and what is likely to be true.
Yeah.
You know,
it takes a while. It takes a while to prove something, and some things are never proven.
And I think it also depends on what is, like if we lived in a universe where life is everywhere and we see oxygen on a planet, then maybe it makes more sense that would be life. But if life is very rare and we see oxygen on a planet, maybe you start to explore other opportunities, right? Or possibilities.
Maybe, but maybe the way to make oxygen without life is more common.
Right.
I mean, we try to sort through all that like a forensics analysis with very little information, but we're getting there.
So most people think about the equation or the framework of trying to understand how much life is in the universe through the Fermi paradox. And I understand you have your own framework, your own perspective of how to do that equation. Maybe, so let's just start at like a high level. Like, what's this framework about, and how can we think about it?
Sure. Well, on the one hand, we think about all the stars in our night sky, thousands of stars. We think about all the galaxies we can't see. You know, there's hundreds of billions of galaxies. And then we think about each galaxy having hundreds of billions of stars. That's just an incredible number of possibilities. If every star has many planets.
Right.
There have to be planets that are the right temperature, have the right conditions for life, and there has to be life out there. But the framework, or like what we're facing today, it's not those hundreds of billions of galaxies and there are hundreds of billions of stars. It's literally like the closest 100 or the closest 1,000 stars like the sun that we can search right now. So right now our framework is more like, we can't know all the people on Earth.
Right.
Maybe you can know your neighbors. You can know your neighbors well, and you can knock on their door and see what's happening.
So the exoplanet research is around these close stars.
Most of it.
Yeah.
I mean, some could be around distant stars, but just in our galaxy, in our neighborhood, basically.
And so wait, how many stars are in our galaxy?
Hundreds of billions with a B.
Hundreds of billions.
Hundreds of billions, yeah.
So impossibly large number of stars, each with their own solar system of some sort. Do all stars have planets?
Most of them. We could say we don't know. Almost certainly nearly all stars have planets. There's one exception though, because remember, we see stars being born and they have these disks of gas and dust. We liken it to like the dust bunnies that will form under your bed. Dust wants to collect, it wants to make planets. But there's just one type of star. It's like, these are very big, hot stars. They rush through their life, they burn energy really fast. And we suspect they may be so big and bright, they just blast away that disk and there's no time for planets to form. That's a bit of a side note, but on the whole,
it's like an interesting anomaly.
It's an anomaly. That's why we can't say every single star has planets.
Right.
We try to be precise in our language, but most of them will have the planetary system.
And do we have any idea how many of those systems, how those stars have a planet that's rocky, that's like in some way similar to, I don't want to say too similar to Earth because maybe we'll get there, but a rocky planet, not a big gaseous one.
I
like
want to
Jupiter.
just go out on a limb and say probably all of them do. But
Yeah.
do we have evidence? People do those numbers. I don't know if I have the latest one on the top of my head, but
It's likely some large percentage.
probably all.
Yeah. Wow. I mean, because that's...
But not
That
all
changes
have
things.
one, we have our Earth,
Right.
which, wow, it's so beautiful here. It's so beautiful in Hawaii. It just feels so, livable. But we need the right kind of planet with all the right conditions, So there could be a rocky planet, but maybe it's too hot for life. We could have a planet, maybe it's too big with no solid surface and deep down it's boiling. So we need to have the right planet in the right location.
And so that's what you're looking for to find a planet that could be like Earth, like a
We
second
have that.
Earth.
We have a planet. We kind of go back and forth on what is it we want? Like,
Right.
what exactly? For me, I'm holding out for the true Earth twin. A rocky planet orbiting a star like the sun in a similar orbit. Planet with oceans and continents and life. But that's a ways off. So in the shorter term, we're like, what other types of planets could be habitable? And we're trying to broadly expand our thinking. It's so hard to do that. We're so, how we're just all so self-centered?
Right.
We like to expand that to terra-centric, like Earth-centric. We just, on Earth, all life needs liquid water. So a lot of people are stuck on, we need liquid water. We have to have a planet the right distance from the star to get the right amount of energy. That's all true. And right now, there's a real push to not stars like our sun, but a different kind of star. Our neighborhood, our galaxy, our universe is littered with small red dwarf stars. They're very different from our sun. They're a tenth to half the size. They tend to have a lot of spots and a lot of flares and activity. But there, we can find and study planets much more easily. Remember we were talking about transits?
Right.
And you were asking, well, how much of the starlight does it block? Well, a planet the size of Earth only blocks 1 part in 10,000 the bright light of our sun. And the atmosphere would be like, 1 part in 10 million or 1 part in 50 million. But if it's a small star, a very small star, now the planet blocks out like 1 part in 100. And the atmosphere will block out 1 part in 10,000. So all the numbers are easier. And that's where the focus is right now, is not to find an Earth twin, but let's call it an Earth cousin.
These telescopes, I guess, by their nature, just must be the most powerful cameras in the world.
So powerful.
Because I'm just thinking about that at a millionth or a 10 millionth of the light that you're
Right.
blocking. That's what you're measuring for
That's
the
right.
atmosphere, right?
That's like, let's measure this table right here
Right.
to 4 or 5 decimal places.
Yeah.
Like, we certainly can't do that now. There is a way to do it, but it wouldn't be part of your everyday toolkit.
Right. You need some sort of incredible
So
equipment.
special. So our special telescope is the James Webb Space Telescope, NASA, ESA, CSA telescope. It's phenomenal.
So what's the next step in building towards understanding around the atmospheres of exoplanets?
Well, the ones around the small red dwarf stars,
Yeah.
we got a little stuck, actually, because it's like if you were to go exploring and you get to a roadblock, or a block in the jungle or a block. And this block, unfortunately, is the stars themselves. They're very active. They have a lot of spots. They give off flares. And the transit method really relies on knowing the background. And if the background is changing, like during transit or from transit to transit, it kind of messes up our methods. So I and others are working better to understand the stars. And a growing number of people are working on how to remove the so-called noise or get rid of the problem or understand the stars better. So that's kind of the short term.
Got it. So it's the star moving.
It's not the star moving, it's the face of the star changing. Think about it like this. Remember how, this we might cut if it's too complicated, but remember how we were talking about we're looking for a change in planet size or change in the drop in brightness as a function of wavelength. I want you for a moment to imagine a planet with no atmosphere. And we think some of the planets have no atmosphere. And the planet is transiting the star. But now the star has a spot. Okay, so the star is actually a little bit smaller than the true size because the spot is dark. But now imagine that spot, it also has a spectrum. It also changes with color or wavelength. So now even though my planet is not changing size, the apparent size of the star is different at different wavelengths because of these spots that have a wavelength-dependent temperature or brightness. So now there's two components. There's my atmosphere, changing in size as a function of wavelength, depending on what's absorbing. And now my star also, apparently, its apparent size changes because of the spots that are different with wavelengths. So now we have this problem. We've got two things we've got to disentangle.
So what are the solutions to solve
Well, there's
that?
one brilliant solution. I got to tell you about this amazing solution. Okay, so there's one system that's everyone's favorite called TRAPPIST-1. And TRAPPIST-1 has 7 planets. We have evidence that the innermost planets have no atmosphere. They were so close to this active red dwarf star that the atmosphere is gone. So if we can get back-to-back transits, the whole system is aligned. So one goes by, it has no atmosphere, and we essentially now can get a snapshot of the star. How does the star change with wavelength? And right following, so before those spots have had a chance to change or evolve or rotate away, we get the planet with the atmosphere coming by next. And so we have a snapshot and we can now subtract out the star contamination. That's the best idea I've heard.
So you get the original star without the planets in front of it, and then contrast that to the planet being in front of it, and then the atmosphere of the planet is what you're measuring.
Close. That's the original idea.
Okay.
That was my original idea.
Yeah.
We have to add on to that to deal with the contamination from the star.
Right.
Because the original idea assumes the star is not changing, which is true for a lot of stars, just not these small red dwarf stars.
Right.
This new idea is you have 2 planets now transiting, one at a time. The first one has no atmosphere.
Got it. Okay.
So all we see is the effect of the star, the spots. But so we take an observation of the star when the first planet's going in front of it. And we can take one of the star by itself. We've got the star when the planet with no atmosphere is going by. So we know the star contamination contribution. Then right after we get the planet with the atmosphere going by. So, okay, in the one case, we have atmosphere plus star contamination, but we also have star contamination on its own. It's actually super complex. It's not obvious as to why that we're doing that, but yeah.
It's incredible to think how far away and how complicated these systems are, and you guys are all tracking them in a way that's very, very incredibly precise. It has to be perfectly precise.
It does. But we also have other things. We love physics and computers, and it's just incredible how far physics has taken us. When we think about our sun, it also has spots, right?
Right.
It has flares. And, we understand our sun extremely well. And my colleagues, Sasha Shapiro and others, they literally can make movies of our sun, like of granulation, that you can't tell the difference between the movie and the real solar observations, actually. And we understand spots and their structure and so many things. And so I'm part of a team that's trying to take those models and make them work for these cooler and cooler stars so we can also make a model of them. So we can make a model of what that contamination looks like the 3D structure of the spots and the light coming off of it and how and why it's changing its flux with wavelength. So we have to throw all of our skills at it. The observational idea I shared, the models that can help us understand from what we call first principles. These are very complex models. They involve convection and magnetic fields and all kinds of things.
So you have to add all this math together to figure out one thing.
One thing, yeah. It's so much work. It's so valuable, precious, our precious planets. We're investing a lot of people power and resources and everything.
Yeah. Let's talk a little bit about Starshade.
Starshade, yeah.
So for somebody who isn't familiar with it, what is Starshade?
Well, let's back up a moment, because this whole excitement about finding an Earth cousin, a rocky planet transiting a red dwarf star, is going to sustain us for now.
Yeah.
But we need to keep thinking of our future. And that heart's desire to find the true Earth twin. Can I just tell you this? I just want to explain it this way for a moment. Have you ever gone on 23andMe?
I have, yeah.
Oh my gosh. You know what? The thing about 23andMe is you have a chance to find like a distant relative. Did that happen to you?
Yeah, so we did Ancestry, and we found there's a bunch of people, like a whole list you scroll through, right?
Well, sometimes you find someone even closer.
Yeah.
Like, I actually found that. You can find like a cousin or a relative. They might be different generation or live in a different country. And I did. And it turns out my grandfather had an unknown affair. So I actually have this aunt, I have a new aunt. It's wonderful. I really have enjoyed meeting her. But anyway, let me back up. So you could go on 23andMe. You can find like a cousin. Maybe they're a different generation. They live in a different country. It's still cool. But let's imagine for a moment. You go on 23andMe, and what pops up is an identical twin.
Yeah, that would change everything.
Well, that's like the difference to me between the Earth's cousins.
Right.
These planets around the red dwarf stars, they're very different from our Earth in so many ways, versus finding the true Earth twin.
A true Earth twin, let's just define this. Like, is this a planet that we imagine that, I know it's impossibly far away, but if we were going to skip that part of it and say that we were to get there somehow, that people could live there, or that maybe with a little bit of changing, they could live there.
I think so. I like your definition. Everyone has their own. I really love your definition of it, yes.
Well, I just want, because Earth feels alone in the universe.
It feels alone, and we feel alone.
Right.
By extension.
But we feel alone because of the way that we talk about it, not necessarily because it's true.
Right.
Right?
When we're looking for these gases that don't belong, so we can infer the presence of life, we don't know what kind of life. Like, it could be just slime, literally just bacteria in a film. We wouldn't know if it's intelligent life or just, bacteria.
Right. Well, I mean, the history of the Earth.
That's right.
The longest period of time was single-celled, followed by the second longest period of time, which was very simple.
Right. So our chance of what we find. Right. But so, I do think of an Earth twin as a rocky planet.
Right.
Orbiting a sun-like star in a similar orbit to Earth's. A planet with oceans and continents and a thin atmosphere, and hopefully
the possibility of life.
The possibility of life.
Yeah. Okay. So this is this thing that we would love to find. But it's impossibly hard to do.
It's impossibly hard because planets are so small,
right,
so low mass and so dim compared to their bright host star, and Earth immeasurably so. Our Earth is 10,000 times smaller in area. It is 300,000 times less massive, and Earth is 10 billion times fainter than our sun in reflected light. So wow, before we were talking about 1 in 10,000, but to find the true Earth twin, it's 1 part in 10 billion. Like, wow. I mean, do you even ever deal with numbers in the billions or 10 billion?
I mean, once you get past that, like, it's a numbers I don't even think the mind can comprehend.
The mind can't comprehend, exactly. But it is so hard. So to do that, primarily we need to block out the starlight so we can see the planet directly if we wanted to study the atmosphere. The transit method won't work because the atmosphere is too small against the backdrop of the big sun. We need to go to space above the blurring effects of Earth's atmosphere. That's kind of like standard thinking right now. Our atmosphere is so turbulent, right? And do you know how stars twinkle at night?
Yeah.
Twinkling is bad. We can't do like a 1 part in 10 billion measurement if we have a twinkling star. It just won't work.
Do stars twinkle from when you're in space?
No, they do not twinkle because it's our atmosphere that's moving it around.
That's fascinating.
Yeah, you know what it's like? Imagine that the star is right up there and the light is coming to you.
Right.
But the turbulence jumbled that ray and moved it around a little bit. And now it looks like the star is, kind of right beside it. Like it's the rays are coming to you, but they're getting jumbled, and it makes the star twinkle because your eye sees the star as being in a different spot slightly.
It's almost like looking through water, and it is
like looking through water. You know, if you're in a swimming pool or underwater and you look up, it's like you see these large blobs.
Right.
It's like that. That's what our atmosphere does to our telescopes.
So we have to figure out how to solve for that.
Yeah, and there's 2 ways to do it. One is we do have a way to correct our atmosphere. We literally can observe bright stars. We have laser guide stars, and we get information about what the atmosphere is doing to that known position, and we can correct the mirrors. We can come back to that later. But right now, the current thinking has been that we can't do that for 1 part in 10 billion. We can do it for other things.
Right.
But if you need to get to that exquisite level of blocking out starlight, we need to go above the blurring effects of Earth's atmosphere. And that's where Starshade comes in.
That's where Starshade comes in.
Yeah.
So Starshade is about... Well, I'll let you describe what Starshade
is a giant specially shaped screen.
Yeah.
It's like a giant flower. And Starshade is tens of meters in diameter. And it would have to go to outer space and formation fly with a telescope. It has to be tens of thousands of kilometers away from the telescope. And the goal of Starshade is to block out the starlight, like literally block out the starlight so that only planet light enters the telescope. And to do that, because remember, it can't block the star and planet. It can only block the star with the planet being so close to the star. It has to be very specially shaped and designed to get the job done.
And so the shape of the flower is a special shape.
Special shape. Because you know what? Now you've got to dial back to physics.
Right.
If you remember this from high school or anyone who's taken college physics, if you block out a point of light with a sphere, let's say Starshade was a giant circular disk. If you block out that point of light, do you know what happens?
What happens?
You actually aren't blocking it. It turns out that the light from the light can act like a wave, and it kind of bends around the edges. So what ends up happening is you would get these concentric rings, like dropping a pebble in a pond. You get ripples. But those light ripples from diffraction are way brighter than the planet you're looking for. So this very special shape of Starshade, like the giant flower,
right,
it's like dropping a pebble in a pond, and the pond being perfectly smooth to 1 part in 10 billion, and all the waves are pushed to the outer edges.
So it's reversing the effect, or it's canceling the effect of the ripples, so that
canceling it,
so that you can see around
in a certain area,
right,
and moving the ripples somewhere else. And it was invented and mathematically figured out in the 1960s, actually. Actually, it's really even more interesting. What the originator figured out, Lyman Spitzer, was, okay, instead of a circular screen, you could have a giant circle, but you'd want to go from completely opaque to transparent, just very, very, very gently, like through that whole disk. But he realized, you can't build that. It has to go so perfectly to get the 1 part in 10 billion. No one can build it. And he realized mathematically that was equivalent to this giant petal-shaped flower-like structure. Isn't that so cool? That with math, he figured out that it's the same.
Yeah, this discovery that you could never have discovered unless you did it.
Mathematical discovery. So Starshade has been a thing, since the 1960s. It's been picked up, shelved, at least once a decade since that time.
And so I'm just trying to picture this. This idea involves 2 things in space: the telescope,
right,
and then the Starshade,
right,
and then it's outside of Earth's atmosphere.
Far outside. It's
going
in
around
fact,
Earth.
No, in an ideal world, no. Earth's gravity makes it very hard to formation fly.
Right.
Because they've got to be lined up almost perfectly. So we want to get away from Earth's gravity. And there's more than one option of where to go, but that's the general idea.
And then once it's out there and it's away from Earth's gravity, it's lined up perfectly, but it's moving, so it's flying, right? Or would it be still?
It would be still just for the day or the days or a couple weeks while it's studying that star. And then when it's finished that job, we have to decide, does it stay there for a while or does it move to the next target? So then Starshade has to fly. It takes 1 or 2 weeks to get to the next target.
Got it. So you're moving this around.
You're moving it across the sky. The telescope can stay stationary.
Right.
Or the telescope can move and the Starshade can stay. But, there's this thing in math called the traveling salesman problem. If you're a salesman or salesperson, and you have a list of places you have to go, let's say across North America, what's your most optimal way to hit all those places in the most efficient way? So we have that same problem. And that would be you have your target star list. What's your optimal way to move across the sky, and how long do you stay at each spot?
Right. Once we're up there, then what happens? Let's say that it exists and that we're looking through the telescope at the Starshade. The Starshade's blocking the light with a special shape.
Right. Well, there's 2 things. One is we hope to know where the targets are in advance. There's other ground-based programs that aim to find the Earth. And so if we know where it is, we know when optimally to look. We go there and we observe the atmosphere. Actually, we'd see every planet in the system at one time, and we would observe their atmospheres.
And then we would get that information back, and that
data would get sent back to Earth. And I would then be analyzing that data and looking for the gases in the atmosphere. The fingerprints, is there water vapor that would indicate a water ocean? Is there oxygen? Perhaps we'd want to see carbon dioxide to know that it's a terrestrial planet like the ones we're familiar with. Maybe it has carbon monoxide instead, or methane.
Is there a signature that would be if we saw the signature, we'd be pretty confident it'd be Earth-like?
I mean, that's a tricky question. We never have absolutes in frontiers research.
Of course, yeah.
So I would be happy if we have water vapor and oxygen in the wavelength range we can see, and also ozone. We want to look in the ultraviolet. Ozone has an incredibly strong signal. You know how we don't get, ozone blocks the most harmful ultraviolet rays. They never make it to Earth, actually, which you might have heard of that.
Right.
But that just means if we're looking at a planet with ozone, there's a sharp cutoff where ozone's absorbing so strongly. Ozone's an indicator of oxygen as well. So I'd like to see that. I'd die peacefully.
So this is something that you've worked on for decades.
Decades.
And
pretty much since I was a postdoc starting out my career.
And I understand that the journey has not been easy and that recently things have changed.
Well, I'll tell you what, I started out always the youngest team member on these big teams that were doing all the concept studies, study after study after study. And I watched the leaders get old. And by old, I mean like late 70s, early 80s. And even one of them wasn't that old. And one day he got up, Roger Angel, a famous, legendary telescope builder. And he just looked around the room and he said, I don't see this happening in my lifetime. I'm moving on. I'm going to work on solving problems on this Earth. And I just never thought I was going to be that person. Like that I would get to that age. I mean, obviously I'm not in my 70s or 80s. But if you can, I don't want to be that. I never wanted to be that person where, I always saw myself as growing into the job of being the leader of this.
Right.
And I don't want to say it out loud,
Right.
So this is a real moment. I don't know if maybe you have a name for the moment, but it's a real moment.
Like a moment where it feels intense.
It's a junction.
Right.
I can keep working on this, or I can change gears. So I think there's only one option.
Right.
So I'm still working on Starshade. Starshade, big projects, they always go through life and death situations.
Right.
And we have a few things going on right now. One is Starshade has been shelved. And there's a few reasons why. I don't know if we can get into all of them. But before we do, I want to just share my favorite analogy of how Starshade works. Imagine you, Zan, have baked me some banana bread for this early morning interview. And you give me the bread and I'm like, wow, thank you. I forgot to mention I don't eat cinnamon. And in this bread, you've put some cinnamon in the part of 1 part per 10 billion. So you have 10 billion particles of flour, or in the ratio. And 1 out of 10 billion is a piece of cinnamon. So I'm like, before I eat this, can you please take out the cinnamon? And what would your reaction be to that?
I mean, it would be impossible.
Well, would it though? What if you had all the money at your disposal and all the best engineers?
I mean, I guess it'd be possible, but it would be incredibly difficult, right? It'd be
okay.
It doesn't seem like.
Oh my God, I love your thinking. I just like watching you think through this. I mean, I'm sure there's a way to do it. If we had to drop this interview and go and figure it out, I think we'd come up with some good ideas.
Right.
But you had decades. If you had decades to figure it out.
I would put it this way. I think most people would think it's impossible. And for the few people that try to figure it out would think it's incredibly difficult to do.
Okay. Well, let's now talk about, you tell me last night, we're going to be starting really early. Can I make you some banana bread? I'm like, yes, but can you please keep the cinnamon separate?
Right.
The 1 part in 10 billion there. Keep it in a separate little dish. And then, is that easier or harder?
What's easier?
Way easier. So Starshade blocks out the starlight. Only planet light enters the telescope. Here the planet light is the cinnamon. We've separated it out before it enters the telescope. It's easier. But there's another way to block out the starlight, and that is inside the telescope. It's a device called a coronagraph. Here, the planet and starlight enter the telescope and are mixed together. It's way harder to separate it out once they've already been mixed up. Just like our cinnamon and our flour are all mixed together, we have ways to separate out, but it's very, very challenging. But for a variety of reasons, that's the path NASA's decided to take with the Habitable Worlds Observatory. The next flagship mission is to do the internal coronagraph, and at least for now, not the Starshade. So it's harder to do. The telescope has to be way more sophisticated in order to be stable enough to block out that starlight inside the telescope once it's already been mixed together.
And just to put this in perspective, the size and the grandeur of these missions, how much does it cost roughly to put this telescope in space?
All these cost so much, it's crazy to even let you know. Our James Webb Space Telescope, although it has a lot of bumps in the road,
right,
it's on the order of 10 billion. And so just to give you some numbers though, I always like to, before we get to the sticker shock, just say, space costs 100 times things on the ground. So pick your favorite thing. Let's pick something right now just to get a number going.
Like a cup of coffee.
okay, so your coffee was $4 because I also bought a cup. So 100 times. So it seems like a lot for coffee, but there weren't any other options. So you're going to spend your $4.
Right.
Let's say you walked in here and the coffee is $400.
Right.
Would you buy it?
No.
Okay. I wonder what a cup of $400 coffee would taste like, though.
Right.
But no, let's pick something else. Like, let's say an electric bike. That's sort of the next level up. Like these electric bikes, because my husband's been trying to get one, they're like $4,000. It's kind of a lot. But you might want to splurge and get a really nice one for $4,000. But what if an electric bike was $400,000?
Right.
That's just so much more. So space is a lot. So I just wanted to put that to you. So Starshade, we have many options. The cheapest option is $2 billion. Maybe we could get that down to $1 billion or $750 million. It's a lot.
And this is NASA. That's the mission.
Yeah, those are like NASA dollars. Everything's going to work, but it costs a lot to mitigate risk. Well, this coronagraph in space, or the current mission under development, it's supposed to be done for $11 billion, but things are usually way more. One of the versions was costed like $20 billion B. So the coronagraph, Starshade involves the telescope and the Starshade. These are expensive, and Earth isn't going to be cheap. Very expensive, very costly. And so it's not just that, it's not just me getting older and not solving it. It's like, do we commit the money? We want it to be our next mission. We don't know if there's going to be enough money to do it anytime soon. And the coronagraph has a long way to go in maturing it. So it's all kind of jumbled. Like, I'm not articulating this as clearly as I'd want to, but that's the problem. The whole thing's jumbled. We don't have the right option.
Well, the question is this going to happen in our lifetime?
Oh, it's going to happen.
Right.
It's definitely going to happen. But my question was a little more selfish. It's like, am I going to be able to lead this mission? And I've realized too, it's not up to me even.
Right.
The powers that be, the high school politics, they're picking.
So talk a little bit about that, because I think most people, me included until we had a conversation recently, don't really understand how people decide what gets funded by NASA. Like what missions are picked?
Well, I can speak for astronomy, where we're very proud of our Decadal Survey. Every decade, for many decades, astronomers get together and they make a priority rank ordered list. And one of the reasons the James Webb Space Telescope made it through all its bumps was because for the number of decades needed, that was number one. And these projects are sometimes 30 years from concept to launch. So astronomers get together and do that. But it's my personal opinion that this no longer works, actually, because we've done the smaller, easier things, and it gets harder and harder as you need a more specialized tool for everyone to work together. Like, let's say you're setting out to do your project, but you can't do it just alone or with 2 or 3 people. You need to carry along hundreds of people, and everyone has to get something out of this. So you can't get your specialized equipment anymore. You have to have a more expensive, more all-purpose equipment. And so what happened was, because exoplanets are so exciting and the astronomy community acknowledged that that's the driving force, our number one choice has to be exoplanets. But everyone has to agree. And there's not just exoplanet scientists in the room. There are also other types, cosmologists, extragalactic. There's lots and lots of kinds of astronomers. So in everyone getting together, and this is my opinion, I'm not saying this is the truth or whatever the historians will unpack it as I say, but what happened was Starshade is so efficient because remember, we're separating out the planet light from the starlight.
Right.
It's extremely efficient. We can get away with a smaller telescope. We could have a 2.4 meter telescope. We could have a 3.6 meter telescope. But that's not big enough for the next step in visible wavelength extragalactic astronomy. It's not big enough. So the Decadal Survey decided to land on a much bigger telescope, 8 meters or 6 meters or even bigger. And in that case, Starshade's not as good because you need a giant starshade. It has to be even further from the telescope. And they also didn't think the Starshade was possible, like at that scale. It's certainly harder for sure and more costly. So they chose to do a big telescope with a segmented mirror that uses an internal coronagraph.
And so who chose? Like, is it like a group of people or is it?
It is. It's a group of people selected to be on so there's it's like a pyramid. There's a top level panel of about a dozen people, and then it flows down into these subgroups. So supposedly everyone's voice get heard. But get this, me being the main Starshade advocate, I'm excluded from being on the top level committee, even though I'm qualified to, because I'm too biased.
You're too biased.
Well, I'm too biased because I was an official leader of a Starshade concept development for a long time. And we had another person. So at the end of the day, you wouldn't be, and again, this is my opinion,
Right.
It's the personalities that win. So the people who can passionately vouch for something,
Right.
You're supposed to be objective, but let's face it, humans are never objective.
Right.
And we had, in my personal opinion again, another key person that I wanted to be on that top panel, 2 people, let's say. They were in charge of a study on exoplanets that was supposed to feed into the Decadal. And one of them said he would only agree to do all that work if he wouldn't be excluded from the main top panel. And they said, that's fine. But when the time came, they're like, you're excluded. So we couldn't have our right people who could really advocate for what we really need.
Wow.
Yeah. And so it just kind of got, I guess, the high school politics of, or maybe everyone wanting to work together, thinking we have to. And I just don't think it's the right path. We call it the Christmas tree approach. Like,
Right.
if everyone needs to do something, it gets bigger and more wieldy and more costly and more complicated. And furthermore, honestly, if you were an extragalactic astronomer,
Right.
you should have picked Starshade, because then you're fully decoupled. You can have your big telescope and launch at any time.
Right.
Starshade can get launched later if needed,
Right.
if it's not working out. But if you're married to the coronagraph, now all of a sudden, your telescope, it's way more complicated than it needs to be, and now it'll be delayed.
Right. So now who knows how long it's going to take for this to get up to speed, and it's
Well,
putting the whole timeline behind
Yeah.
what it would have been otherwise.
And especially with the current massive uncertainty about NASA's future, we just don't know. So it's gonna be put off. And the other thing I realized, look at this. I think this is something really sobering. I also set up my life to be able to be chosen to lead. So what does that mean? I have initiated my own tiny space telescope from concept to launch. It was called Asteria. It was a CubeSat, eventually implemented and operated by NASA's Jet Propulsion Laboratory. But I started that. I got it through. I was also number 4. In a startup, you have I was number 4 on the MIT-led NASA mission tests. It's still operating. I've stepped down after the prime mission finished, but that was a mission to find these Earth cousins, actually, that we could follow up with the James Webb Space Telescope. So I've done everything I could to put myself in the position. And it turns out that's not enough, actually. I didn't realize, why am I so naive at this level? It's not up to that. I could have everything be perfect and still not get picked, right?
Right.
Maybe that's obvious to you and others, but I just didn't realize that people will just pick their friends, or they'll just, overlook you or do something for whatever reason. We have this big thing now called, I don't know if we should get into this on here, but the DEI,
Right.
it actually made everyone equal. And so your accomplishments, achievements, having learned all those lessons the hard way no longer matters, it turns out, in many ways. Maybe that'll change.
Yeah.
So yeah, it's like a complicated world, and I've set myself up to lead Starshade specifically. I'm keeping Starshade alive.
Right.
ProjectStarshade.com. And we'll keep it alive until it's ready to get revived, just like it has decade after decade.
And I think it's also important to think about the context of your life, of how much personal sacrifice, because in your book you talk about when your kids were young and spending this time where you are spending all these hours working on this dream. And so just
right.
Can you tell me about what that was like?
Right. I was just thinking of a funny memory. I'm not sure if I should share it. It sort of makes me look bad, but should I tell it to you?
Tell it and we can cut it.
All right. So we have, I had just a wonderful, wonderful life. I am just looking back, just so happy. Even in bad times. I was a widowed single mom. But I had the most wonderful people that I, again, intuition found and brought into the fold. I had these 3 young women, Diana, Jessica, Veronica. They were babysitters, but honestly, they're like family. And Jessica at one point and Veronica at another point lived in my house, in exchange for helping with the kids. And the kids adored them, and they were adored back. So we were usually never there together, right? Because if the babysitter was there, I was out. But one night, it was the Boston Red Sox were about to win the World Series, and we let the kids stay up late. And Veronica and I were both there because, World Series was on. So we're hanging out, and one of the kids is just so happy, even happier, because he's like, I'm just so, he's just beaming. He's like, it's so great. It's like I have 4 moms. And he's smiling. And then he looks at me for a moment. He's like, but you're not one of them because you're never around. It sounds so horrible. I just take that as like, wow, okay. He's obviously just trying to push my buttons here. I mean, it wasn't like I wasn't around. He was just found a moment to like let me know. I think I was a great mom, if you want to know the honest truth.
Yeah.
My kids are grown up, healthy, happy, strong. They're honest people. And I think we had a wonderful life.
There's something to be said about sometimes when it feels hard, you can really find love deeply. You know, I know your parents were divorced. My parents were divorced when I was a kid as well. And there's actually one passage in your book that I found really powerful, which was the story of when you had to tell your kids about their father wasn't going to make it. And this, if I remember the story, is when you were on the way to the zoo.
Right.
And there's just something about that passage that just felt so human, right? Like,
yeah.
What's something that's something that no one ever prepares for, right?
Well, no one would want to prepare for it.
No one would want to. I know you said that you rehearsed it, right?
Because, he was, my first husband, Mike, he was very sick for very long. And I just learned so much about human nature. Like, oftentimes I'd want to sit the kids down and give them an update.
Right.
And they wouldn't. One of them would cover his ears and run out of the room. And then I found something really amazing. Because, throughout history, no one ever told kids anything. Did your parents ever sit you down and explain stuff? Rarely.
Mine did, but my parents were probably like you, so.
They usually don't. So what I discovered was if I had a friend over, let's say Zan, you were visiting me, hadn't seen you in a while, I'd be like, wow, Zan, I need to tell you, I'm going to update you about Mike. Like if I had that, all of a sudden the kids are eavesdropping and they're really interested. And then I'd be, here's the deal. And then as soon as I finish, okay, they'd go play or whatever. So I'm like, okay, maybe throughout history, kids only learn from eavesdropping, and these kids are hardwired to not accept the message from me directly. So then I realized I could just, if I needed to tell them something, you might not know I'm doing this, but I would make sure to give a somewhat sanitized version of what's happening, and I'd let them eavesdrop. And then after they were done eavesdropping and left, I could give you the real scary story.
That's super interesting.
It's so cool, so cool.
For me, it makes me think when you're a kid, your imagination allows you to kind of not be in the same kind of reality as the grounded reality you are when you're an adult. And so I wonder if hearing something and eavesdropping allows you to kind of process or play with the idea.
I think so.
Whereas if your parent, who is this world of authority, tells you directly, you have to accept that as ground truth.
Maybe.
And that's heavier.
But anyway, so I was thinking about when do I tell them that he's terminal? You don't want to tell a kid too early, right? Because they'll just mull it over and, as you said, use their imagination. It might go the wrong way. But you can't tell them too late either because you want to give them a bit of warning. So I literally waited and waited and waited. And I also had to have the right moment where I just had their full attention. And I did. We were on our way to the zoo, and it turned out, I'd say Mike was maybe 6 weeks out in the end from dying. But his brother was visiting. And the kids love trains. You kids love trains.
Right.
We'd often, just for a Saturday morning, take the commuter rail to South Station where the big trains that go to New York City are and just get a muffin and watch the trains and then do the reverse. So we decided to take the train to Rhode Island, and Mike and his brother drove. So we actually met them later. So we're on the train waiting for it. It's just the three of us in this booth, and thought how to tell them. I was like, how someone in our family is really sick. You just have to wait for them to get there. And the medicine's not working. Pause. And your dad's not going to make it. And then one of them, the older one, Max, he just said, well, I already knew. Because remember, he'd been eavesdropping, and I hadn't actually said this to anyone, but he had figured it out. And the younger one, Alex, being younger, he's like, what? He just I thought you were talking about Minnie May, our cat. Because a year earlier, our other cat had died, and we had done the same thing. And he just was in so much shock about this. He just hadn't seen it coming, actually. And it's just really, really, really tough. I just want to tell another story you might fit in later, but, kids do have their own normal. One day, Mike came down to the dinner table, put his head down and fell asleep. Got up and looked around. He was kind of dazed. He's like, okay, I'm going back to bed now. So I look at the kids to just take their temperature. I was just not going to shove on them that something's a disaster here. Although an adult would realize that's not a good sign.
Right.
So I'm just like, so do you think your dad's really sick? Or is he normal? And you know how brothers do? Maybe you had this. They looked at each other, and in unison, they just said, normal. I was like, okay. It wasn't like I wasn't aiming to correct them. I was just trying to figure out where they at in their thinking right now. And so that's why probably he was so surprised.
Right.
Because it's like a slow change in his life. It's just normal to have that.
Right.
It's just traumatic, really.
Yeah.
I can look back and laugh now because I'm distanced from it. It's just like crazy. You know, this crazy.
Well, I think that something else that you talked about that I think is really powerful is how to cope, and particularly the things that from the outside may seem weird or uncomfortable, and like I think dark humor is a really important part of that. I mean, I've seen that in my life. Like, you know, you go through something super hard, and then like there's a moment maybe with like loved ones where you're talking about somebody who died, and like you make a joke that like an outsider would think it's like morbid or inappropriate, but like it was the right joke at the right time to break that tension.
So true. Like one time I'd always wanted a lot of kids, like 5.
Right.
But it just didn't happen. And part of it was because I was so ambitious and just having the amount of money and emotional space to like raise children. And Mike knew I always wanted more, and he wouldn't do it because he didn't want another one. So one day we were just hanging around, and I'm like, we knew he was dying. I just, you know what? I can have another kid now. Because I just was young enough, I could squeeze one out.
Right.
But there was no thought of like how or with who would that happen. And he just looked at me and laughed hysterically at me. He's like, Sarah, you need another baby like you need a hole in your head. Just thinking of all that was to come, like dealing with him dying and like being a widow. It was just unbelievably funny. Because, you know, that's my heart. I wanted a baby. But like, how on earth would I have a baby and do all this? Oh my God, it was just insane to him.
How long has it been since he passed away?
It's been a while. It's so long that I have to think about it, actually.
Yeah.
So let me just do the math. Like 14 years. It'll be 14 years this summer. Jeez, I can't believe like a lifetime has passed.
Yeah.
It's so crazy, right? You know, death is really special. And oftentimes women will have a birth plan, and, you know, they want to have the perfect birth. And I had the perfect birth, actually.
Yeah.
I just wanted to do birth with no medication and have my kids be drug-free when they were born. And the first one took a long time to get born. It's a bit tough. The second one, he just was born. And I didn't have like a single tear. I was the person who the next day it was like, aside from being a bit sore, like back to normal. Perfect birth. Like, wow. It was amazing. Honestly, I wish everyone could witness or do natural childbirth. It's just phenomenal. And do you ever hear someone talking about death?
Not in the same
Well, I'm going
way.
to talk about it now. I'm so proud of myself.
Yeah.
When I look back at my life, one of my single biggest accomplishments is helping Mike have the perfect death. Like, I wish more people would have the conversation. We wanted him to die at home. And we did have a big house, fortunately. So, you know, people didn't have to watch him die, like the kids, namely. But, you know, his doctor, it was insane. The doctor just said, one day Mike came home after having his doctor's appointment. The doctor's like, you shouldn't die at home because you have kids and stuff. It's like, what? Like, I can't go there now because I'm not angry about it anymore, but I was just so furious.
Right. And this is
So
after you
angry.
talked about it with him.
Yeah, we'd already had a plan and stuff. And he's like, I don't know why I think he was telling me because, you know, he agreed with me. I don't know why he told me. It's like, that's ridiculous. What lesson would we be teaching our kids? Like that we just dump someone off somewhere to die? I was just like, I wish I could still cry about it now, but I'd be like, no, you're going to die at home like we planned, where we can love you till the day you die. And, you know, he was separated from the kids, so they knew he was there. It was enough. I didn't have to have them see him, although there was this really intensive moment where I told the kids, now's the time. Like, this was after the conversation that he was going to die, and do you want to say goodbye, you know? It's so hard, right? I bet they don't even remember this. Like, and one of them, no, like he just couldn't handle it. And one of them's like, okay, so he goes and says goodbye, you know, but the dad didn't really realize. Okay, let me just stop crying. But obviously I wanted to make that space. So the days go by and we got this amazing home hospice nurse, Jerry, who was like an angel. And he helped us like get through the whole process, and he would come like every 2 or 3 days, and there were other people. The hospice program's amazing. You have to die within 6. I'm just trying to make some humor now to make it a little lighter.
Yeah.
But if you don't die within 6 months, you get taken off the program. So
That's wild.
well, you have to. It's someone's paying for it, right? So
Sure.
it's sort of just say you can't trigger it too soon is what I'm trying to say.
Got it. So
It's
you have
like
to
we
do
had
it
to
right.
wait till the right time, and
Yeah.
we definitely had the right time. We had a really scary moment, and he got on hospice. It was so wonderful because the regular doctors just aren't on the ball. Anyway, these guys are good with pain, and Jerry was amazing, and oh my gosh, Mike was so strong, and he was hanging on. Like he just wouldn't die because they'd never seen this. Like unless it's the 20-year-olds with brain tumors or the war vets or the Marines. Like he was so tough, and his body was so healthy that he was supposed to die, and like days turned into weeks. And Jerry just told me I had to tell Mike it was okay. It was just so hard to like, I'm gonna be okay, even though clearly I wasn't. I had to let him know that. So time went by, and he was just taking forever to die, and I'm just like, this isn't just my story, but he was just in a bed. Like we had a hospital bed, and I got some nurses' aides to help like watch him, because even though he was dying, like at any moment, he was a big guy. He could stand up and like get up and be like, where am I? And like step out and topple over. Like it was, but he had an amazing moment. And I just want to tell you something. I haven't told too many people this, but I was like waiting for him to die because it was so important that I would be with him. And I'm at home doing laundry, and we had like the second floor laundry room, and the hair on the back of my neck went up. And I rushed into his room, and the nurse's aide was there. And I'm not going to say it's like all psychic and stuff. It's not. It's like when you finally start to die, your body just releases like gas and stuff and fluid, right? So something in my mind was like really tuned to this. And I go into the room, and she stepped out, and I just was with him. I just watched like the last breath. So, I mean, like how great is that to like help your best friend at the time, like on his most important journey. So important.
Right.
And after that, it was a bit of a disaster for a while. But the reason why I told you that whole story, because after that, after I've taken my, partner, father of my children, until then, my best friend I'd ever had, I helped him have the most perfect, peaceful end. What could be more important?
Right.
Like, do you know?
Oh, I mean,
the way I told it on
know.
purpose
No,
like that, like,
yeah.
I honestly didn't know what could be more important, actually. And I then had a
a gap or
a moment, like a very long moment. And I still think about that moment, actually. And we each have that, that was a very intensive one, but everyone has that at some level. Like, why are you here? What is your purpose?
Right.
How can you make a difference?
Finding meaning
and purpose. So I definitely had that in a big way. And there was another thing that happened after he died, was like you're just so drained emotionally. It's like having no money in the bank. There's just no reservoir. So you just don't do stuff. Like, often we're kind of self-guilted into just doing other people's emotional tasks or just doing stuff for other people. Like, no, I didn't do any of that. All the kind of chatter and useless small talk and the crap. Nope, not going to work for me. You could invite me to, like, okay, it sounds bad, but help out at a volunteer thing. No, thank you. Or invite me to a party. Nah.
Right.
And so you have this clarity of mind now. Because you know what is meaningful versus what is not meaningful. And it changes the game, actually. So for a while, and I try to hold on to both of those things, to like what's meaningful, how do I live every day purposefully, and keep that clutter away. And that's what I try to do to be purposeful. And that's why finding the other Earth, finding a sign of life beyond Earth, finding life beyond Earth, I take it really seriously as my life's mission.
If you had to do one thing before you die, have you thought about what the answer to that would be?
Well, I'd like to find another Earth before I die.
Yeah.
Or make it possible. Like, if it's not me that finds it, set it all up so it can be found and identified.
Right. And so you have this one singular goal that you've spent so much time around and built towards, and
say it.
And I mean, I was just saying, it's hard. It's impossibly hard for most people. It's so many different levels to it. You have the most, you need all these things to line up. And it seems from the outside like odds are against you.
It does. And it seems that, like I was saying earlier, I could do everything right, but it could be the powers that be. It could be that NASA takes a hit in funding for a long time. It could be that the popular high school kids now running the show decide to take a really complicated path,
right.
like the coronagraph that, we are trying, it hasn't been demonstrated to work in the lab yet at the level needed. Like, it could be that this path just slows us down. We all do it. We all go
right.
down the wrong path for a while and then correct. But I might run out of time. And I'm trying to sort through all of that. And that's hopefully in Hawaii at the beach, I can have a bit of time.
Right.
But it's, I don't let it get me down for too long, but it's hard to realize that these decades-long project, and then I don't have infinite decades.
Right. So it's the feeling of the preciousness of time, the one asset that's limited for all of us.
Yeah, and also just like Mike's story, none of us know when it is our time.
Right. And I think that like a theme throughout this has just been like superhuman hope.
Yeah.
And belief. Like, can you speak to that? What allows you to have that hope where other people would have given up?
I don't know. I was about to say, really, other people would have given up. Like,
right.
I don't know. I mean, there's all kinds of people out there, like my funeral director, who I became friends with.
Yeah. Great
guy. He's such a community guy. One time I bumped into him in the store, and everyone felt about him the way I do. Just saw everyone go up to him, and yeah. He said a lot of people don't do that. They just walk away when the person's that sick. I don't know. I mean, I don't know. What do you mean they would have given up on what, though?
I mean, you stayed with your husband till the very last breath.
It's really
you
great.
Stayed with this project for decades when other people, I mean, even if you think back to Exoplanets at the beginning of your career,
right.
You took this project that like seemed impossible and you followed through when people like, you had the haters and you had the doubters and you had the people saying this isn't going to work. And you just were relentless in the fact that you're going to find a way.
I think I'm hardwired that way. I really do.
Yeah.
I just don't have another explanation for it.
It's just in your blood.
I think it's in my blood, but it gets amplified, right?
Right.
Like, I think we all have a propensity for certain things. And then just your childhood and as your life goes by, well, in physics, we call it like a forcing function. Stuff happens and it will like amplify those certain parts of your personality, I think.
How did you persevere through all of this?
Well, oddly enough, I do study people in a lot of detail because being autistic, like looking back, I didn't understand people. So I had to like force myself to understand them. And, along the way one thing that happened when I was really little and my parents were first divorced, my dad had this lady who came in, Mrs. Petek, to like help when we were there on the weekend because we were like toddler age kind of, or maybe a bit older. And he pulled me aside and was like, look, I don't approve of what she's been doing because she talks about her dead husband every other sentence. Like, oh, Mr. Petek used to pour his tea like this. I don't know, somehow that stayed with me. And later on, even, you'll meet people who are widowed and the dead person's still with them. Like, the dead person's always with us, but the dead person's with them like in every other sentence.
Right.
So I sometimes realize I don't want to be that person, but is there a way that I can not be that person? Some widows, they're derailed for life. Others bounce back. So I had to actually give it some careful thinking. How do I stop thinking about them all the time? Eventually, like I moved the picture away from the living room, but there's a lot more internal work I had to do. But there's one really key thing I want to mention. It's what I got from my dad, because out of all his crazy theories, one of them I actually liked. It's called The Power of Positive Thinking. And he was really big on this book. I'm blanking on the author's name. It's some famous book from like the 1950s. And I remember he gave this book to me when I was 9, and I decided I'm going to have to implement this. So every night before I went to sleep, I didn't believe it at first, okay? But you have to believe. You can't just say stuff. I'm like, I had my happiest years with Mike, like the first years together. If I had to be like the best friend I ever had, I just like say to myself, someday I'll have a new best friend. Someday I'll be happier than before. And it's not about being bad to the memory of Mike, right? It's like the power of positive thinking, because when you do that and it gets so deep inside of you, I think it just opens you to opportunity. And I do have a new best friend, Melissa.
Right.
I have this fantastic best friend. She's now been my best friend for over a decade.
Yeah.
And I've been my husband, Charles, I got the big love. And, I'm not saying that power positive thinking will solve all your problems, because it won't. But
Right.
it's just about how do you persevere? How do you bounce back? How do you hold on to the thought? And how do you make it real? It's not just an accident for me. It's a purposeful thing.
And Melissa's somebody that's been with you for a decade now, right? Or
Yeah,
close
Melissa.
to it.
Yeah.
There's a story of her giving you a stone that you kept in your purse.
Oh, right. So the widowhood's a complete disaster.
Yeah.
There are meltdowns,
Right.
public meltdowns. There are days that are rock bottom, awful. And during one of these days, after I became friends with Melissa, I just called her and I couldn't get a word out. I was just crying. So Melissa dropped everything and came to my house. And, this happened more than once.
Right.
She would come and explain to the kids how it'll get better soon, or.
Right.
So she gave me a stone, this rounded stone. And she just said, put this in your purse. And when you're rummaging around to find your keys or your phone, you'll find this rock. And when you touch it, you can think about how time smooths all edges.
There's something to be said about finding a core group of people who believe in you and can be there for you in those important moments.
So true.
And I think that throughout your life, you've talked about different ones. I mean, you had your professors before, and Melissa.
Right. And the widows.
And the widows.
Yeah.
And the good news is that your story does have a happy ending. And not even an ending, but a happy turn to it, right? Which is that after years, you did find new love.
I did.
Can you tell us the story of how you guys met?
I can. Well, first of all, there is this sort of old wives' tale that widows are way more likely to remarry within 2 years. I think as the years go by and you're older, you just become more fixated in your ways. I mean, I don't have to rationalize it. It's not even
Right.
maybe true. It's just a thing. So I'm basically up to my 2-year mark after my first husband died. I'm on the plane to go on yet another trip, to a meeting that maybe I don't even really feel like going to. But I felt like going to it until I realized it's the July long weekend and it's another weekend away from the kids. Although they're more than happy to spend the long weekend with Jessica.
Right.
It's all good. I'm on the plane my 2 years are up. It's too bad. I get to the meeting and it's an amateur astronomy conference where I'm the keynote speaker. It's the Royal Astronomical Society of Canada. It's where I got my start in astronomy, seeing the moon through a telescope when I was little. And they have different chapters all across the country, and once a year they meet for a general assembly. Not everyone goes, of course. So I go to the meeting and I'm billeted by a widow because they don't have money to put you in a hotel, so you stay with another member. And we go into the evening reception, and I get to the reception of this amateur astronomy conference, and across the room I see this tall, dark, handsome man. And I'm just like, wow, I have to meet this guy. And Charles is kind of staring at me, and we definitely connect somehow. And throughout the weekend, I'm just waiting for him to come and talk to me, as an amateur astronomer, as the professional astronomer who's been brought in to give a talk and mingle. And a lot of the amateur astronomers are coming to talk to me, tell me about their telescope. It's cool, right? It's what to do. It turned out Charles was the president of the Toronto Centre. And they operated a big telescope, I want to say it's 74-inch telescope. It was serious stuff here. And he had only decided the day before that he was going to go to the General Assembly. It's optional, but if you're president of one of the big chapters, you probably should be going. Long drive to Thunder Bay, Ontario. But he was too shy, also having this spark, it was a bit awkward. So on my second or third day, my widow host was busy. She's like, do you mind because it's a lot of work to take care of someone. She had to go do an errand. Do you mind if I just leave you alone? And I'm like, that's fine, of course. But I got a bit lost and I couldn't find lunch where the lunchroom was. So finally I get there and everyone else has got lunch except Charles is there and maybe one other person. And he had come back to get a salad. So then he's forced to talk to me, right?
Right.
And he's like, Dr. Seager, that was a great talk. It was just so funny. So awkward. And he's like, well, would you like to have lunch with me? I'm like, sure. So we take our trays, it's cafeteria style. We go to the far end away from people in these big windows. And I sit down and all I can think of is, wow, I finally get to talk to this guy. And I'm just beaming at him. And he will say in that moment he knew his life was going to change. And that was love at first sight. Just like the movies, but it was an amateur astronomy conference.
Wow.
And then it took a while because I lived really far away and I wasn't really ready for like anything, still, widowed and all that. And he was getting divorced, so we couldn't really do much for a while. And we just became friends. It's the best way to start a relationship, is just being friends from afar. So if I just felt like I was, needed a break, just close the computer, he's gone. Yeah, so a few months after that, we decided to try it. And we went, it sounds like really right out of a fairy tale, but we lived in different cities because he lived in Toronto, I lived near Boston. And so he said, I'm going to the UK on a business trip. Do you want to join me for a few days? So, for most single moms, like, that's not happening, especially over New Year's. So I called Jessica. I'm like, Jessica, you know how you've always wanted to go to the Caribbean? Can you, I make it an offer she can't refuse, okay?
Right.
I'm like, do you and Veronica, their sisters, do you guys want to take the kid? It's on a holiday for the, clearly I'm burning through cash here, which is a widow's prerogative if you can. Do you guys want to go over the long week, for some time, take the kids to the group? And she's like, that would be so fun. Yeah, let's do it. So now I'm free, right? Because the kids will be so happy. They're not even going to know I'm gone. Oh my gosh. So I go to the UK and there's Charles. We spent 4 days together and it was just totally amazing. And just to tell you how great he is, I'm just waiting for my first kiss, okay? Because I'm like, when's something gonna happen here? And he's so shy. And just not to be TMI, but when you're older, it's kind of hard to start dating again.
Yeah.
You're divorced, you're widowed, you've been with the same person forever, and maybe you met that person. I met my first husband, I was in my early 20s. It's what happens, I'm waiting for my first kiss, and I know he's really stressed because the pressure's on to make it a good kiss. So one night after dinner, it's pouring with rain, and we're walking through London in winter. It's so cold. It's January. And before I know it, we're standing in front of Buckingham Palace. And he's just, Sarah, you are my princess. And I got my first kiss.
He must have planned that out.
Oh my gosh. We can ask him.
Yeah.
Must have planned that out for how long, right? I mean, how did he make it happen? The restaurant was not too far away and
right.
Yeah. So we get home and I get a really awkward voicemail, just well, we should have made plans. I don't know. Because when you're dating and it's obviously this is a big deal.
Right.
It's a huge deal, but you don't want to be ghosted, or you usually, okay, if you're the guy, you should, I'm not being, I don't know whose role it is, but it would be good to have a plan and not just leave it hanging.
Yeah.
So he gets back and he's like, oh, I'm really sorry. We should have had a plan. I should have made a plan, but would you like to get together? And it's of course. So we had to do the weekends back and forth. And literally 6 weeks after that London trip, we're in Boston. It's his first visit and it feels so right. And I introduced him to the kids and we're spending a weekend at the hotel, just so we can have a night off. And Jessica, of course, is babysitting that weekend. And we're sitting at dinner and he just starts talking about, we're going to do this in the summer and next year. I'm like, okay, for those dating, you don't just talk about, you don't want to jinx it, right? So you're not going to say, hey, 6 months from now, you can come to my cottage, or,
right.
You don't do that. So I was trying to explain to him how let's not go there right now. And before I know it, there's this long, long pause. Nobody's saying anything. And then he just blurts out, Sarah, will you marry me? Just like that.
Yeah.
And
you said yes.
I said yes. And it's great to be older. There's no one in my life to say, do you want to think about that?
Yeah.
It's just my choice.
And how long ago was that?
That was a while ago. It was a while back because right now we're also in Hawaii to celebrate our 10th wedding anniversary.
10th wedding anniversary.
Where we got married about 10 years ago. 10 years ago in April, we got married.
Wow.
Yep.
And so this trip to Hawaii is meaningful for a couple of reasons.
A lot of reasons. I mean, admittedly, one doesn't usually go to Hawaii unless it's a very special occasion, right? So we have put a whole bunch of special things together. It's the Venus instrumentation. It's our 10th wedding anniversary splurge.
Right.
We have some friends we're bringing here, some family friends, to help them see the green flash. We have I have some other astronomy work related to the Keck telescope and things like that. We have to talk about Phosphine and Venus and how that, because it's that whole story of now what?
Now what?
Now what? Well, there's another problem that happened to me as well, swirling all with Starshade and the cost of the mission and the NASA and astronomy community realizing whatever mission we pick, we don't have enough money to jumpstart it right now.
Right.
So whatever it is, it's a problem. And I had another problem, actually, a big problem. So remember, we want to find a sign of life on an exoplanet by studying the atmosphere and finding a gas out of equilibrium, out of context, that we can assign to life. And so with this in mind, in 2007, wow, that's almost 20 years ago, I embarked on wanting to know every possible gas that could be a sign of life. So I and the team I gathered, we looked at every molecule that is in gas phase at like a temperature and pressure conducive for life and started going through them. There's 14,000 gases, actually. There's maybe a few thousand legit gases. Then there's ones that are like the halogens, fluorine or chlorine, that make it really light. It would be like attaching a balloon to something. But if you have these lighter molecules, you just get a lot. So there's a lot of gases. We work through it and try to figure out which molecules have a unique spectral feature, that aren't overlapping with water vapor or carbon dioxide. Like, do they have a unique place where they're absorbing light at a wavelength? Which gases on Earth are not just coming out of a volcano?
Right.
Or, are produced by non-life. And then we ask, can it accumulate in the atmosphere? Because sunlight, ultraviolet especially, destroys gases. So we're looking for gases, those three things. And, almost pretty soon after starting this project, came across what is now my absolute favorite gas. Remember, Earth only had oxygen for part of its history.
Right.
And moreover, that oxygen was only at the high amounts it is today for an even shorter part. So it behooves us to find all the gases that could be an option. We need to be ready so when we observe an exoplanet, we know what we're looking for, or rather when we see something, we know what it means. You want to know what that gas is? It's called phosphine. So phosphine is a phosphorus atom, P, attached to 3 hydrogen atoms. Now, the reason why most people have never heard of phosphine is it's extremely rare. We humans make it as a pesticide. Life on Earth makes it, like bacteria in oxygen-free environments. So people culture it, they take it to the lab, and they will see phosphine. So it's poisonous to us humans. It's bad for life that needs oxygen. It just doesn't go. But it's not really produced by anything else. There may be a few obscure ways to make phosphine, but no.
So it's not coming out of a volcano.
It's definitely not coming out of a volcano.
And so why is this your favorite gas?
Because it checks all the boxes. It has no false positives on Earth. It means it's not made by non-life. It has unique spectral features. So its spectrum is not dwarfed by a gas like carbon dioxide or water vapor, something that should be there already. And it can more or less accumulate. It's not super resistant to ultraviolet light, but it's good enough. So those are the 3 reasons. So my team was working on phosphine. We published some papers on phosphine as a biosignature on exoplanets. We published a few papers about phosphine on Earth. Because, by the way, phosphorus P, on Earth, it goes with O, oxygen, as phosphates.
Right.
It doesn't go with hydrogen because we have very little hydrogen, and it takes energy to make phosphine. So we put out these papers, we give talks, and lo and behold, across the ocean, someone else is working on phosphine as a sign of life. It's a complete surprise that another astronomer would work on such an obscure gas. And that professor is Professor Jane Greaves. And she purposely wanted to search for signs of life on Venus. So she searched through the literature to see what gas might make sense. And just out of the blue, she picked phosphine because it has a transition, an energy transition from its ground to first excited rotational state at radio wavelengths, where she's an expert astronomer. And remember we talked about the investment portfolio? As a scientist, it's kind of fun/good idea to take a small portion of your time and just blow it on something risky. High risk, high payoff. So there she is searching for signs of life on Venus with phosphine, and someone connected our 2 teams. And she generously invited us to join her team, actually. And we joined her team. She already had a signal from one of the telescopes in Hawaii called the James Clerk Maxwell Telescope. It was a bit of a dicey signal. It wasn't super robust. But we joined her team. We helped her propose for a more sophisticated telescope called ALMA. And we joined her team.
So just taking a second here, this gas is something that we can see in the atmospheres of other planets, or that we believe we can through the signatures that they leave.
Yes.
And it's a gas that on Earth isn't created by anything except for life. And so 1 plus 1 together, 2 is that this would be a good indicator.
A good indicator.
that there be
So
life.
there's always a few caveats. I'm blanking on what the obscure things are on Earth that do make it without life. There are one or two really obscure things, but they're so insignificant, I don't even bother remembering them.
Yeah.
There's that. And number two, we actually see signs of phosphine gas on Jupiter and Saturn. But those planets have a lot of hydrogen. They're mostly hydrogen. And beneath their atmosphere, it's super hot, and phosphine is favored to form. It's the favored form of phosphine. And it gets like dredged up by convection. So we do see it there. On Earth, we don't see it, much of it. There's only trace amounts. But yes, it is something we have observed in conditions where it should be. And yes, it doesn't appear to be makeable in like large quantities without life. So yes, it checks all the boxes, and that's why we're super excited about it. So, ready for the story of phosphine. So a few years go by, and this team, led by Professor Jane Greaves in the UK, reports on the detection of tiny amounts, parts per billion, of phosphine in the Venus atmosphere. And the team works out all the ways phosphine could be made on Venus. Lightning, meteorite delivery, volcanoes, and in 100 pages, no way to make even the parts per billion that we reported detecting. So we did not say there's life on Venus. We did say we're reporting the detection of phosphine gas, and there's no known chemistry, leaving room for unknown chemistry, but there's no known chemistry that can produce it at the levels detected. And therefore that leaves room for the possibility of life in the Venus clouds.
So let's talk about life in the clouds on Earth. Like if I look up at a cloud right now, is there life in these clouds here?
There is. There's bacteria that are swept up from the surface. They don't want to be there, presumably,
Right.
but they get swept up. They go in the droplets for a while. As those clouds move, they're transported, sometimes across continental scales, and they get dropped back out.
So if I were to take some device and capture a bit of
People
that cloud.
do. They sometimes send like a balloon up with rods,
Right.
and then they bring it back down and they culture it. That's how we know there's life up there.
And
You
so
get life.
we think that there might be life in the clouds of Venus.
Right. Well, it's a little more complicated than that. But yes, I mean, we think there could be.
There could be.
Like the surface of Venus is too hot for life.
Right.
Everyone will agree on that. But just like on Earth, when you hike up a mountain, it gets colder and colder, and so too on Venus. And so the idea that there might be life up in the clouds of Venus where the temperature is just right for life, that idea was thrown out there by Carl Sagan over half a century ago. And, at the time, they didn't know that the Venus clouds, they're not friendly, made of water. Those clouds are made of a very toxic substance, concentrated sulfuric acid. It's like deathly for any of our life. But nonetheless, the idea has persisted because, life needs a liquid for molecules to react and have chemistry for life. Life needs energy like the sun, and life needs the right temperature for complex molecules to form. So, theoretically. So let's go back to phosphine for a moment, where made this report, and what do you think happened? Like, do you think people are like, yay, there's life on Venus?
No, I mean, I remember the report coming out, and that's not really what happened, right?
It's not what happened at all. I mean, just like scientists are supposed to be skeptical by nature, they were. But there was a lot of angry skepticism. People got really upset. And it's controversial to this day, very controversial. A report of phosphine on Venus was extremely contentious. I could even say trashed at every level. Well, first question, is the signal real? It's a tiny signal, right? Imagine an analogy, you take a photo and there's just this little thing. What is that? You have to analyze the data. You've got to really draw that signal out. It's tough. No one's going to claim it's not a hard situation. Astronomers took our data. It's all public. Some of them recovered the signal. Most of them did not recover the signal, okay? So that's bad news. But it's a tough thing. It's not like a giant signal that's obvious or someone would have found it already.
Right.
But using the James Clerk Maxwell telescope data, people did recover the signal. Second question. Let's assume the signal is real for a moment. Is the signal attributed to the right gas? Is it indeed phosphine? Or could it be another gas? Only one other option in the vicinity, sulfur dioxide. So the team that recovered the signal wanted to claim it's not phosphine, it's sulfur dioxide. I mean, there is sulfur dioxide coming out of these volcanoes and volcanoes on Venus. We argue it's not that. We're still arguing the signal is real and that it's not sulfur dioxide. For the moment, let's just, for argument's sake, adopt that the signal is real, that it is phosphine. Then there's all the people who want to say it's not made by life, but here's other ways we can make phosphine. And all of those papers, by the way, someone on the team has refuted at some level. But it's still incredibly controversial. And it will live on as a controversy for a long time. But let me put it this way. While I was telling this whole story, now for a moment you're me. And I just spent like almost 20 years on like, what are all the gases that could be made by life? We want to do Starshade or something else and find signs of life. Well, are we going to believe it on an exoplanet?
Right.
After everything I just told you about Venus, our planet next door.
Right.
Like, are you? Are you going to believe it?
Because Venus is like so much closer to us than an exoplanet.
So much closer.
Right. Like how could we think about that in terms of the distance between us and Venus versus us and an exoplanet? I mean, is there even a way to, I'm trying to conceptualize
these
this.
Exoplanets are trillions of times further. It's beyond a number we can get our heads around. You know, like the nearest star is light years away. You know, 1 light year is 6 trillion miles. Whereas Venus is maybe light minutes away, not light years. So it's what a few minutes is to a few years, or what's a few minutes to a decade in time.
Right.
That's I think we can understand that. Like a few minutes is from now until our next topic.
Right.
But a decade? So long.
And so your whole thing is that if they're not even going to believe it now, when we have this what you believe to be very compelling evidence, then it's like, how is the world ready to believe it when we have this signal from so much farther away?
Right. And so that's a career crisis right there.
Right.
Right. I mean, I'm happy for a reason, which
Right.
we're getting to. But yeah, I mean, that it wasn't really like, I like to think I have a tough skin. So, okay, people are going to complain and be haters. Okay, that's just part of life. So it's not so much that the haters or the people angrily unpacking all this, the controversy. It's just, what does that mean? You know, am I going to spend the next, whatever time I've got left in my career, hopefully it's 20 years, could be less. Am I going to fight like this extreme battle, or am I going to do something more real, more definitive?
Right. So what was your answer to that question?
Well, the first answer is you have time to do more than one thing, right? And
Right.
projects ebb and flow. So my first answer is, how could we follow up on Venus? Not about Phosphine. How could we go to Venus, send missions to Venus to find out directly whether or not there's signs of life or life itself?
Right.
And so while the Phosphine story was, even before we reported on it, I leveraged this opportunity actually to get a group together to think about a blueprint of to what would we do if we could do it.
To go potentially find life on a planet in our own solar system.
On Venus specifically, something that's been overlooked.
Yeah.
And what's really interesting about this is it's so crazy. Like sulfuric acid is an insane chemical. There's reasons why people don't think there could ever be life in the Venus atmosphere in sulfuric acid. And it's a giggle factor. Like, do you ever have a project, you tell it to someone or a plan,
Right.
and they just start laughing at you? I bet you've had that.
Yeah, absolutely.
Yeah. And so we have this thing, it's supposed to pass the giggle test.
Right.
But for most people, they can't take this seriously. So NASA, ESA, like the large government agencies, they're not going to be able to look for life on Venus. It's just too crazy.
Right.
So when you think about it, it's something that I can do in 15 years, something that people don't want to do. Other people don't want to do it. We don't have these large committees. We don't have the politics deciding, can I do this? Can I get the forces, rally the troops, get money, get the project, get the job done? It seems like a no-brainer.
And we've been to Venus before, like
Lots of times. NASA sent an amazing mission to Venus, a probe, in the late 1970s called Pioneer Venus. It separated into its 4 components and went down. Former Soviet Union sent over a dozen probes in the 70s and early 80s. They sent 2 balloons to Venus that lasted for 2 days on their battery power. I mean, we've done a lot. There have been orbiters since that time. But so far, we haven't gone into the Venus atmosphere for nearly 4 decades.
And so help me understand, and I know this is a series of missions, but what do the missions look like and the progression of us being able to say, okay, we send something to Venus, we collect what we need to collect, and if there is life there, we prove it?
Well, we came up with 3 missions, small, medium, and large, short term, slightly longer term, and then long term. And the idea is that each mission could build on what they find. And there could be a space where if you find nothing, you're done, which is fine if we can answer the question. It's always hard to answer something definitively as a no. So the first mission, oh, by the way, we used to call ourselves the Venus Life Finder missions. But there's so much pushback, it just makes people, it was just too distracting for people.
Right.
Because there's very interesting chemistry, whether or not it's life. So people are willing to go to Venus. They want to go back. So we rebranded to Morningstar Missions to Venus. And that has many meanings. Like one meaning, sometimes you see Venus in the morning sky shining so brightly, like a new dawn is rising. Another thing is in complementary to the big government missions that take decades, could we envision a new way to do space science? We have smaller, more focused missions that are cheaper. So we're trying to do that as well. And so that's why we call ourselves like this new Morningstar. So Morningstar Missions to Venus conceivably has a few missions. The first mission we call the Rocket Lab mission to Venus. We've teamed up with Rocket Lab, where I brought the science instrument and science team. And Rocket Lab is doing the rocket and cruise and probe. Cruise vehicle and the probe itself. That's why we're in Hawaii. We've completed the instrument. It's built in Colorado at Droplet Measurement Technologies. And we have two. We've got our flight instrument and our flight spare. And we've brought the flight spare, put it on a drone, and flew the drone as the volcano was erupting the other day. The VOG went over to where we were about, I want to say maybe 10 miles that way. Or actually, I don't know which way.
Is this the VOG here? The smoke
you can call
that's
that
coming
VOG,
out? Yeah.
But this VOG might get blown the wrong way and there's not enough of it. We were really lucky that Kilauea was giving the big eruption.
Right.
Because where the team was with the drone was just perfect. Flew around, collected data with our instrument. And we also did some ground truth sampling. So we're going to try to ask ourselves, what is in this VOG? And then see if that matches up with reality based on our instrument. And what the instrument is it's a nephelometer. So it shines a laser through, on the probe it'll be through a window, and looks for fluorescence, autofluorescence. Like if you think of a nightclub or a fun house for kids, like you know how when it's all dark but your clothes light up from the UV light. And if there's autofluorescence, it's very cool because it means it's not pure concentrated sulfuric acid. It means there is likely organic material inside those droplets. It doesn't mean there's life, but it means all life needs organics. So it's a good step forward. We're also measuring the backscattered polarized radiation. No particle in nature scatters equally in all directions. I don't know if you knew that, but if you went around shining a light at everything, nothing scatters equally in all directions. And water doesn't. We've all seen a rainbow.
Right.
It's bunching up the light and spreading it out at the same time. So encoded in how light scatters radiation is information of what the particle is made of and what its size is, and its shape actually. So by getting this backscattered radiation, it's partly been done before, but we have a more sophisticated way of doing it. So we'll confirm and extend on past. But this first mission, it's a very small, relatively cheap mission. So it's like throwing a rock, a very fancy rock at Venus. The probe will get dropped off. There's no parachute. It's just going to slow down from its own drag and take these measurements during its 5 minutes in the cloud and confirm that the clouds are more than just pure concentrated sulfuric acid.
And if they confirm that, then that triggers the next mission.
It triggers the next mission. But the next mission will happen either way, because what we really want to do is go to Venus and identify what kind of molecules are there. Not just that there are organic molecules, but which organic molecules are in the concentrated sulfuric acid. And for that, it's more complicated. We want to go to Venus, likely with a balloon mission, and float around in the atmosphere for a week and collect the clouds. We want to have the cloud particles condense on our cloud catcher and by gravity shake down into a reservoir, then evaporate the sulfuric acid for whatever hopefully is left over, deliver that to our mass spectrometer and see what's there in terms of what kind of complex molecules are present.
And so what's the time frame for somebody if it's somebody who's not in this field and they're like, okay, there's the possibility that there's life on Venus. There's these missions that are going to go and be able to give us information that we might be it might come back and we'd be very not surprised, but many people would be surprised, but they might find it. Help me understand what that time horizon looks like.
Honestly, that's always a question of money. If we had enough money, we would just get the job done in a decade.
Right.
But it sounds like a long time if you're not in space science, but in space science, that's like no time. So Basically, the Rocket Lab mission to Venus is anticipated to launch in the summer of 2026. Okay, and so the next mission, our balloon mission to Venus, we're looking at like a 2031 timeframe. And while everything is moving forward now, we can do all the prototyping and the tech demos and build and test and find signs of life on Earth using our Venus instrumentation. We can get that job done, but it's a pretty hefty price tag to actually build a mission that works and that gets to Venus. So that's 2031. And after that time, if we do everything right and we're strategic and we have the right instrument and there is life there, we'll have, like, we won't be sure there's life there, but we can be really confident that we need to get the final proof. And the final proof, honestly, we're not going to believe it until we see like little bacteria visually.
Right.
So it's either going back using a very special microscope, or what we'd really like to do that's hard and hasn't been figured out yet is bring a sample back to Earth.
Mm.
Yeah.
But we've taken samples back from, have we taken samples back from Mars?
Not yet.
Not yet.
We've brought samples back from the moon. We've gone to asteroids. The Japanese twice have gone to an asteroid and brought stuff back. NASA brought stuff back from an asteroid. Brought stuff back from,
So it's possible.
It's definitely possible. It's possible, but it's, we're waiting also for other technology. We want to bring samples back from Mars, and that would solve a lot of our problems.
Mm.
Yeah.
It's incredibly exciting. I mean, I think that when you think about the math of how many planets are out there,
Yeah.
it seems impossible that life is not out there, and maybe it's everywhere. But until we see that evidence, it's like it's always a shadow of a doubt. And I feel like that's going to be a fundamental shift in how we see the world.
We just want one other example. And then we'll, if life originated on its own, independently from life on Earth in at least one other place, we can have confidence that life is everywhere, if it's that easy for life to form. But before we wrap this up, there's just one more thing. And that's the journey and the joy of scientific discovery.
Yeah.
It's like literally absolutely insane. But in part of this mission, what we've been doing is laboratory science to demonstrate that there could be life on Venus. And it's just so crazy. Like, just to tell you about why we know our life cannot survive in sulfuric acid, the way I got started in the lab work was during the hot pandemic summer.
Right.
There's like nothing for kids to do. My older son, Max, was 17 at the time, a teenager, no jobs for kids, sports fields are closed. So I put him on the Venus project. But the project I gave him, it was like an online assignment. He actually finished it within a few days instead of the few weeks I was expecting. And he pushed to do real experiments. So we discovered that, so I said, okay, fine, we'll try. We can set up an outdoor lab on our porch and be as safe as we know how. So it turns out that you can't order a lot of sulfuric acid to your house. It's that dangerous. But you can order a lot of little bottles. A loophole I hope is still around. So we ordered a lot of little bottles. And we just started out very generally on the porch on like a warm day. I want you to imagine for a moment, you're a teenager, bored, hot pandemic summer. No one is sick, fortunately, so you can be bored. What are you going to put in sulfuric acid? You're just going to experiment with anything around you. You're looking around. What are you going to put in sulfuric acid?
Well, I'm probably going to, I don't know, maybe like an ant like that.
Yes. Before I could say, please don't do that. The ant was in sulfuric acid, had a seizure, turned to goo instantly. I mean, if that's not enough to convince you that our life can't survive in sulfuric acid and why people are so horrified to even entertain the idea there's life in the sulfuric acid clouds of Venus, I mean, I don't know what is. So it's just so crazy. But he tried a lot of things that summer, like the rhododendron leaf is very waxy. Not too bad. Then put wax from his braces, pencil lead, graphite is fine. I mean, there's a surprising number of things that actually are okay. And then later, 2 years later, he was then an undergraduate studying biochemistry. Needed a summer job. He actually found a summer job, but then he could still do this part-time. We started studying chemicals and biochemicals and concentrated sulfuric acid. Now, although some of them are unstable, you'd be surprised the number that are stable. We took our 20 biogenic amino acids and put them in sulfuric acid. Stable. With one exception. Some of them are chemically modified, but they're stable. Our DNA is unstable, but part of the DNA, the latter part, ACGT, stable. I mean, that's just the tip of the iceberg. It's absolutely astonishing to us and others. Wow. And some of this work dates back a long time when people studied sulfuric acid just for the sake of it.
Right.
They didn't put a comprehensive picture together. They didn't know that Venus had sulfuric acid clouds. Some of our work is new, wasn't done before. A lot of it wasn't done before, but really amazing. I don't even have time to summarize all how great it is, but it's crazy.
And what this means is that this sulfuric acid, which previously everyone was like, there's no way that life could exist in there. Now, what you've proven through these experiments is that the components that make up life could exist. And so even though DNA itself, in the structure we know of it on Earth, can't exist there, it opens up this door of possibility.
It does.
That some other fundamentally different type of DNA could exist in that
And
atmosphere.
that's what we're trying to do. We're trying to synthesize in the lab that a kind of DNA, by swapping out parts, is stable in sulfuric acid. So I can convince you and others that it is worth spending the big bucks to go to Venus to search for life.
Right. We talked earlier about how through the process of this experimentation, you made another discovery, a liquid. Can you tell me a little bit about that?
I can. I just love the lab. I've become a lab chemist now, and I have my own lab, and I have a team of people, amazing young people working in the lab. And one of them, remember, we're building instrumentation to go to Venus. We want to collect the clouds. We want to evaporate the sulfuric acid to see what's left and analyze that. So we're prototyping everything in the lab. Now, sulfuric acid, it has a really high boiling point, but you don't want to boil it to evaporate it because it will destroy the chemicals you're looking for.
Right.
So instead, I'm not sure if this rings a bell for you, but we're making a very low pressure chamber. Because if you hike up a mountain, the boiling, I don't know, maybe that's not the best thing, but anyway, we have to make a low pressure chamber so it's easier. The sulfuric acid can evaporate at a lower temperature.
Right.
So she set up this, one of the postdocs, Rachna, set up the system, puts like dirt in sulfuric acid, evaporates the sulfuric acid, recovers the dirt, etc., etc. Until one day she's looking for something new. Remember we talked about the amino acid project? She finds my amino acids. I feel like when you're in the lab, sometimes you're like, please don't touch my stuff.
Right.
But fortunately, I hadn't put a label on, please don't touch my stuff. She took the amino acids and put them in sulfuric acid, evaporated this excess sulfuric acid. And surprisingly, she didn't know what was going on, but there was just this tiniest bit of liquid left over. Tried another amino acid, same thing. Tried another one, and honestly, most people would discard this. They would throw it out or say something's wrong and just move on to another compound or try to fix their equipment.
So liquid left over after what exactly happens?
After hours of evaporating the sulfuric acid. After, remember, the earlier experiments, she put dirt in, evaporated the sulfuric acid,
so it's an evaporation chamber. It's basically designed to evaporate everything. And even despite it supposed to evaporate everything, there's something remaining.
Yeah.
Right?
Something remaining. There's like a big pump and like a tube and like a glass jar with a lid.
Yeah.
And the glass jar is sealed. So we're like taking air out of that glass jar. So it's very, very low pressure inside. And then putting that on a hot plate to heat it a little bit. And the sulfuric acid usually goes away. It usually evaporates and it can go through another tube out to the fume hood, or it often will condense like on the top of the jar. But just getting rid of that sulfuric acid. And if you just put sulfuric acid by itself, you'll get rid of every last little bit. All gone. And wouldn't go away, mixed with an amino acid, a nitrogen-containing organic compound. Wouldn't go away, and didn't know what it was. And fortunately, did not throw it out, but brought this to me and Janusz Petkowski, the main team member in biochemistry.
And what was it?
Well, it turns out she had rediscovered a compound called an ionic liquid, actually, and some of us knew about this compound, but we had just forgotten about it because other people at MIT work on this. But what was new about this is it's an ionic liquid made out of planetary properties. And what is an ionic liquid? It's like a salt. It's like your table salt, but it's a liquid at room temperature. And what had happened was acid wants to donate a proton. And sulfuric acid is an incredibly strong acid. So it donates a proton. And by the way, nitrogen wants to accept a proton. And just FYI, Max and myself and Janusz were the core biomolecule and sulfuric acid team. We already knew that because remember I told you about the nucleic acid bases?
Right.
ACGT. They were all getting protonated on the nitrogens. So somehow we could have figured this out, but we hadn't thought about it. So sulfuric acid is getting rid of a proton and it's becoming negative. The proton's getting added to the amino acid nitrogen. That's becoming positive. So you have a negative and a positive, and they actually glue together like two magnets. And supposedly, didn't know this, so strongly bonded that what regularly a bit of heating and low pressure would separate it, won't separate it. And it just remains a liquid. And some of these in vacuum, they supposedly could last for thousands tens of thousands, millions, even a billion years in outer space.
As a liquid.
Supposedly. I'm not, like, don't hold me to that, but I've been digging to find out how long could it last exactly.
So this is a liquid that doesn't evaporate and that is very stable. And why is that important compared to like water? Water evaporates, right? So what's the meaning or the significance of this?
Well, the significance is that, remember we were talking about Earth cousins?
Right.
Think of like the Earth black sheep of the family. It just means there are other planets that could have life if life needs a liquid and the right temperatures.
Right.
All of a sudden now, earlier on we talked about atmosphereless worlds. Remember that?
Yeah.
We talked about planets so close to the Red Dwarf star they may have lost all their atmosphere due to the star heat early on in the star's life due to high energy radiation. So if there's a way this liquid can form naturally, sulfuric acid comes out of volcanoes, actually. Like the site we were at yesterday, there's a sign that says there's sulfuric acid here.
Right.
Okay. So we have sulfuric acid. These organics are very common. They are on asteroids. We don't know exactly how they form, but if we had some pockets of, like when water evaporates and you have salt left over.
Right.
Imagine you have these pockets of organics, nitrogen-containing organics. You have your volcano giving off sulfuric acid. It lands on this, evaporates, makes an ionic liquid. You have a liquid now.
So you could have a planet with ponds of this.
Ponds, yeah, or puddles maybe.
Or puddles, and you could imagine that these puddles have been there for, I don't know, forever.
We're still working on that.
Potentially.
It could be that ultraviolet radiation helps them break down.
Right.
They might have to get regenerated, but they are very stable. It's not like on Earth, if you had a puddle, it would go away. We all know that. So yes, it's that planets with thin to no atmosphere that we just thought were boring old dry rocks. Wow, they might have life. And these ionic liquids, some of them, they are, including ours,
right.
They are friendly. They're hospitable to biomolecules, actually. So we're just onto something here. We don't know where this is going to go, but it's like it's going to go somewhere. It's incredible. We're doing so many experiments on ionic liquid now. It's breathtaking.
So I want to ask you a question. Let's say that somebody who's watching this is a billionaire, right? And they have the funds to be able to help with these missions. What would your message be to them? What are the missions that they need to be aware of? I want to put together a section where it's like, this is the part that they need to hear.
Well, we can get to Venus for, remember the 100 times more than on the ground?
Right.
Cost. We can get to Venus for 200 to 300 million, and we can tell you whether or not there are complex molecules that could be associated with life. We can do that, and we know how to do that. We're beyond prototyping most of the components to get that job done, and we can get it done.
And that's the amount of money that some people have.
They do. Now, if you wanted a sample return, that's a whole other, that's $1 billion. That is so much. But for $1 billion, Zan, I can offer you some Venus clouds in a vial. Put that on your mantelpiece and have a piece of Venus.
I want to talk a little bit about Starshade. Where's that project sit today? And what's the future of trying to find an exoplanet and Earth 2.0?
With Starshade right now, there's still a tiny bit of money trickling to close out the activities that have been going on for the last decade or more. There's a small amount of funding to be working on what could go with Habitable Worlds Observatory. Like, it breaks down to components. Like the pedal is being worked on at Stanford, a big pedal, which should be part of a big Starshade. I still have a team working on some Starshade science. Mostly we're just advocacy. We're writing papers. We're trying to socialize how Starshade is so efficient. So that's kind of where Starshade is at. It's really not funded right now to move forward. And Habitable Worlds Observatory, that is to use the coronagraph. We just don't have a lot of money at NASA right now. There are studies ongoing. There's some design work being done. There's coronagraph maturation in the lab, which is really needed. So there's stuff happening, but it's just so slowly. Yeah. And
you have this other idea that we spoke of. Can you tell me a little bit about what that is?
Yes. There is a brainchild called Orcas, and this brainchild is Eliade Peretz and John Mather. Mm-hmm. They're both at Goddard Space Flight Center at NASA. And their idea is a way that we could find another Earth using large ground-based telescopes. But their idea is not necessarily geared towards another Earth. It's just would enable that, actually. It's part of it. But what it is this. We were talking about the blurring effects of Earth's atmosphere and how astronomers know how to correct for that blurring. You need a really bright star shining down through your telescope so you can measure the turbulence in the atmosphere and correct for it. And by correcting for it, you have a little mirror somewhere along the optical path with literally physical pistons that move up and down and distort that mirror, like to oppose the distortion of the light from the turbulence.
So this is to de-twinkle the twinkle of the star.
It's to de-twinkle the star, actually.
Right.
It's been used for a long time. At the telescopes here in Hawaii even, they have fake stars. They have lasers on the ground that can excite the sodium atoms in a sodium layer and make like a fake star. But none of those fake star natural guide stars enough to get you to that level we need for the Earth twin, to the 1 part in 10 billion. And we honestly used to say if you were going to make a fake laser for that, it would cost the same amount as sending the Space Telescope system up to outer space. Like, you need such a powerful laser, you just couldn't do it from Earth. But the new idea, it's not my idea. This new idea, by the way, also originated from Professor Kerry Kahoy at MIT. This idea is to have your fake star in space on a satellite. And that way it can be way brighter than anything you could generate from Earth, actually. And you could have an orbit and change the orbit so you can be near your target star. As long as you have to plan it in advance, as we were describing,
right,
your targets and the order you're going to do them in. But in order for this to in order for it to work for another Earth around the sun, it's a lot of things have to go right. We have to be able to position this extremely bright fake star on a satellite, like as close to the target star as possible, so it gets the same line of sight path through your telescope. There's a lot of things that have to go right. But this new project I'm involved in, it's like a stepping stone to what we just talked about, actually. And this new satellite, this new idea, it's called Orcas. And already the team before I've joined the team, I recently joined the team in a leadership position because they need a scientist who's had success behind them to help envision the science goals of this first satellite to do the job. And I'm partly here in Hawaii to go and visit the Keck telescope. It's our 10-meter diameter aperture ground-based telescope here in Hawaii. And the Keck telescope team has been incredibly generous to the Orcas project. Before I joined, they've done several things to demonstrate how it could work, that it does work, and how amazing the observations will be. And the team, through Eliad Peretz and the Keck team, they actually worked with an actual optical laser in space. It's up there for another reason, but they managed to commandeer the telescope and have it be that fake star and show that it can work with the Keck adaptive optics system, actually.
So let me just see if I get this right, which is this system starts with a massive satellite here on Earth. And this
telescope. It starts with a
thank you. Yeah.
Diameter's everything because that helps you separate things out on the sky.
So it starts with a massive telescope on Earth.
Yes.
And the telescope is positioned on top of essentially this mechanism that has pistons that...
Not quite. So it could be like that, but instead of having the whole massive telescope have that, you can take the light that hits your mirror and goes into like an optical path inside your instrument.
Got it.
So you can put actually something pretty tiny.
So the instrument...
Yeah.
Here,
the adaptive optics system, let's call it, the instrument, yes.
Got it. Is on this thing
it's
that's
on an
able to
instrument
move
attached to
very
the
precisely.
telescope. Yeah, the little mirror moves very precisely.
And so, I'll take a step back. The mission of this whole thing is to be able to see exoplanets that are going around a star that are, it's fair to say, trillions of miles away.
Yeah. Well, the eventual goal is to do that. We have to do some easier science cases to get there.
Right.
Yeah.
But this is the theory, and so when that happens, we have to de-twinkle the star because it goes through the atmosphere. Right. And so I'm just kind of doing this step by step, is that there's right now, if we put a laser from Earth into the sky, then we can use that light, not theoretically, you do this, there's limitations, which we'll talk to you about in a second, but you can use that laser, which is a fake star, to say this is stable, and then you can de-twinkle the star that way.
Yes.
But the problem is... Mm-hmm. Sorry, the problem is that is not bright enough.
Right. So we can do that now using a natural star, a star itself. We can do that using the laser on Earth that shoots up and makes a fake star. As long as there's a bright star somewhere in the vicinity, we can do that. But those are not bright enough because we have to get information to correct.
Right.
And if you don't have enough information, you can't correct well enough.
So you need
and
a
the
laser.
information is the brightness of the star.
So you need. So we're talking about space lasers. You need a laser from space to shoot back, and then we're going to use the telescope and this mechanism. The mechanism is going to use the laser coming from space as a strong enough signal to orientate itself in such a way to de-twinkle the star, meaning to account for the atmosphere of Earth, and therefore be precise enough to see whatever you're looking at, which eventually will be planets around other stars.
Yes. And for that eventual case, even though Keck is so powerful and amazing, we need to go to the next level.
Right.
And that would be the ELT, the European Extremely Large Telescope that is 39 meters in diameter and being built right now in Chile.
Right. And so...
But this is all doable in the 15 years or 20 years.
So in the next
Very
15
doable.
years, because let's take it back to that question, which we said earlier on, which is like, if you had one thing to do before you die, and I think your answer was to find another Earth.
It is. That is my thing. And that is why I've joined this project and I'm working so hard. And partly why I'm here in Hawaii, to meet the people, the director of Keck and the deputy director, because they've been so great to the project, to introduce myself as one of the new leaders and to get their support for the next step.
And is this a $1 billion project?
No. It kind of, the best projects, right, are ones that you can leverage.
Yeah.
So the fact that the ground-based telescope exists already, that the new ground-based telescope is being built, I mean, the adaptive optics system would have to be upgraded. Because if we get more information, we need to be able to use that information. We need a faster computer. We need more actuators. So the satellite itself, including the laser and operations, is about 35 million, or maybe even less, actually. So that satellite probably been, if we did it right and it lasted long enough, it could probably be the one to work with ELT. But we may need a second generation. But the good thing about this project, we don't have to invent anything new. Like Starshade, coronagraph, still have some development to do. But the spacecraft that we would want to buy, it's already been built, already exists. The laser, people have done a lot of optical communication from space. Lasers already exist, have already flown. In fact, it's very straightforward.
Yeah, I mean, it's within the realm of what can happen. And it must be exciting where you can see where things working out.
You can see things working out. We can see this. Now, this won't get us to the 25 or 50 Earths that the Decadal Survey would want us to get.
Right.
It won't get us like zillions or whatever, a good number, but it will get us enough, right, to keep the search going. Surely I just have to find 3, even 1. Hey, wow, they're out there. They're around our nearby stars. Let's get momentum for the next mission that could find the 24 of them.
So much of your life has anchored to this unrelenting hope and belief. When people say, it's not possible, or
I don't
the
go
way.
there. No. I've been trained by my dad to never, ever, not even go there. When I finally was offered a job at MIT, I was 35 years old, offered a senior position like with tenure. That's a really big deal at that age. And my dad was dying of cancer. And one of my last conversations with him, I was trying to be proud of myself. Like, it's the best I can do. I got MIT, top university in the world, tenure at 35. And before I could even finish, just acknowledging, it's really hard to acknowledge when you're doing well, say it out loud. My dad just stops, pulls the car over. Remember, he's not well, got cancer. No, I never want to hear you say it's the best you can do. I do not want you to be limited by your own thinking. It's like, wow, that was his ongoing and final message to me. So maybe it's partly internal that I was born that way, but it's definitely, thanks to my dad. I'm not even allowed, he would get mad. I don't know if your dad got mad at you, you don't want to get in trouble kind of thing.
Right.
It's I'm not going there. I'm not thinking that way. I'm trained to never to not do that, to always have the positive. It's always possible. There's always a way. And if it's not me doing Starshade, someone will do Starshade, mark my words. It's too great of an idea to not happen. And if I'm not going to do Starshade, I'm going to find another way. And right now, that way is the artificial star on the satellite.
What's your message to somebody who's young, who maybe is going through something, and who's like, hey, this is the moment where I see what Sarah's done, and that's just such tremendous hope and fortitude, and just what are the words of wisdom that you'd say to somebody in that moment?
Well, trust your inner voice. Find the people who believe in you. Cut out negativity and toxic people. But the most important thing is to, if you can do this, is to do your best to find something you love doing that you're also good at, very good at, and that pays the bills. Like, that is really the ultimate. Because finding something you're good at that you love doing, it doesn't feel like work and it pays the bills, then you can actually do it for your living. As sort of just larger advice for young people, it's really about confidence. You don't want to have like false confidence and go out and try something that's just never going to work. But you really also want to have confidence where it's deserved. And many people, it's in human nature, it's natural to not try because you lack confidence on it. So my message too is to build confidence. Find whatever way works for you, but really what it is thinking about your past success and not just sweeping those under the rug, or we're culturally raised to like not dwell on any success, right?
Right.
How many times do you beat yourself up over failure versus take a moment and be proud of yourself for what you've done? It's so important to take those moments because that's how you build confidence. Inside, you'll know, well, I've done it before. A small thing even. I can do the slightly bigger thing next, and then bigger and bigger. So my message is to find a way to build confidence and to own it.
Do you think that that sparkle in the eye that we talked about earlier, do you think that's something that you're born with or something that you can create?
I think everyone has it, but it is a matter of matching up to the right thing. And not everyone has that match up with something that's a vocation. But we all have it for something.
Right.
We all have it. And sometimes it's just a matter of, I don't want to sound too preachy, but putting your phone away, turning the TV off, and I look at my phone a lot. I love binge watching TV.
Right.
But there's the time to find that thing for you. And if it's not going to be work or it can't be turned into a job, then you have to carve out enough time to do that, to have that spark stay alive.
Right.
A lot of people, the spark goes out. And that's not where we want to be.
It's these tiny signals. It's the
smallest lights in the universe. You've got to find them and hold on to them.
Right.
And grow them.
Which I have to say, that your book is really incredible. Anyone who's listening to this, I definitely recommend to check it out, because I think, the story is not just about the whole journey of your professional career, but it's this journey of life. And one of the things that I really was impactful for me was how, you work in a field that I think from the outside feels so foreign and sometimes impossible for other people to imagine. It's like, oh, yeah, of course, there's these scientists and we're at this volcano and that's amazing, but that's somebody else doing something, right?
Yeah.
But when you have these moments with your kid, raising your kids, and their father passing away, and you realize you're like, we all really are just people. And even people that are superhuman in certain aspects of their life have all these very moments and times, and it's like the minutes that we live are really all the same in some really core fundamental way.
I agree fully.
Yeah. Thank you, Sarah.
Thank you so much, Sam.